Thank you everybody that already joined for the 7 a.m. SASAMI. Welcome for 16 SASAMI meeting with Mr. MarkCloos. In front, maybe we have a discussion and presentation for 1.5 hours with Professor MarkCloos. And MarkCloos is, we have a resume here. MarkCloos is a professor in Department of Geological Science at the University of Texas, Austin. And he received a Bachelor in Geology from University Illinois at Urbana-Champaign in 76 and PhD from California, Los Angeles in 81. So major field project over the years have been the California Coast and Highland, West New Guinea. Major publication concern of mechanic subduction zone, tectonic of our continent collision zone, and the origin of Porphyry-Type ore body. Thank you everyone for joining. So please welcome Pak Budi for opening speech. Pak Budi, take your time for your opening speech. Thank you.
Okay, thank you, Pak Ocha. I was actually intending to read Professor MarkCloos' CV, but it seems like that he has already done it. So good, thank you, Pak Ocha. First of all, we would like to express our gratitude once again, and will be again, to Professor Mark for his availability to share his great experience in the porphyry, especially today. He's going to talk about subduction zones, magma generation, and porphyry-type copper and gold and copper and moly deposits. So we would learn about how the copper moly deposit form in the Cordillera, which in Indonesia is not quite common, but maybe somewhere in West Kalimantan. If everybody maybe has ever worked in that area, there is a small prospect copper moly deposit there near Pontianak. Maybe somebody could discuss later on with Professor Mark. We would like to also express our gratitude to Mine ID, PT Freeport Indonesia, and Freeport McMoran, Copper and Gold, because Pak Sugeng Widodo, which is our senior in our organization, and Pak Wahyu Sunyoto as well, both gentlemen very supportive to the activity program of the organizations, and because of their efforts, they could convince Professor Mark to always be ready to share with us. So we hope that today we could learn something more, something new, something that could inspire us to make a new discovery, to relook, revisit, and probably revise our thought about the how the porphyry, copper, gold, and copper moly deposit could form in our 17 kilometers length of metallogenic belt in our country. Thank you very much for everybody that has joined the session this morning. I know this is very early morning in Indonesia, and it's almost evening in Texas. But I believe that, you know, with this technology, we could actually overcome the hurdles of all the issues of space and time. Okay, Pak MarkCloos, you would have about 1 hour or 1.5 hours to present, and then as before, we will have questions and answer afterwards. Okay, but I'll stop my
Okay.
sharing and then you could hear us.
Here we go.
Okay, thank you Pak Budi for opening speech early this morning. Thank you everyone. And before Mr. MarkCloos' presentation, maybe one of the SASAMI co-member, Mr. Andi Yahya, will have opening speech also. Mr. Andi Yahya. Halo, Pak Andi.
Thank you, Mbak Ocha. Good morning, everyone. Thank you for coming to our speakers. And today we have Professor MarkCloos from University of Texas Austin. And I will give this time for Professor MarkCloos. Please, Professor Mark, take your time.
Okay. Should we begin?
Yes, Mr. MarkCloos, it's your time. Thank you.
Okay. Thank you. Selma Pagi.
Selamat
Halo,
pagi.
Pak.
Hey, good morning.
Yes, and it's the evening here, but it's the morning time in Indonesia. And today I feel very fortunate to be able to give a presentation on a topic. I have a major paper that is coming together, but you're going to see the presentation before the paper is fully together. You may have already noticed that I changed the title slightly. It's instead of Subduction Zone Magma Generation, Convergent Margin Magma Generation. And I'm hoping that you can see my pointer. Can you see the pointer? Is that working?
Yes, Pak.
Yes,
It's
just
working.
Okay, very good. Well, there, Convergent Margin Magma Generation, porphyry, copper, gold, and copper molybdenum ore bodies. And the issue of why some of them have got copper, obviously, is the major metal, but the secondary metal is gold, and why sometimes it's molybdenum. And every once in a while, some deposits have both, but most of the time it's either copper gold or copper molybdenum. And when I first got interested in the issue of how these types of deposits form, this was one of the very first questions that I had as to why? What is it that makes these two settings are so similar in many ways, but in terms of the economics of having a deposit as a mine, it makes a big difference whether your secondary metal is gold or the secondary metal is molybdenum. And I suspect most of you are well aware that in the Western Pacific, the association with gold is more common, but in South America and Western North America, it's the molybdenum. So the issue of why. And this has been something that was recognized about 40 years ago, but really in the last 20 years, it's become apparent that this is very, very true. I'll show you the evidence for that. Now, the other theme that I will have here is the discussion centered obviously on Grasberg district, because I believe that this is one of the most important districts on the planet. We understand quite a bit. I talked about it a lot last time, but today we're going to focus more on making the magmas. What's going on at convergent plate margins to make magmas that can be mineralized in such similar yet so fundamentally different ways. So let's, what's happened here? I try to advance, but I'm not going forward. Where am I stuck? Oh, here we go. Okay. The obviously this is the famous Grasberg mine. I hope many of you have had the opportunity to visit it. It is truly extraordinary, and I view it as it's the most important deposit on the planet. Obviously, for Indonesia, it's the #1 deposit, but the fact is we understand so much about what happened here. And this famous photograph taken by Aditya out of a helicopter at 20,000 feet elevation, you can see the Great Grasberg Pit. But why do we know so much about it? there's so much to be seen of the geology. Look around the surrounding area here. The limestones of the New Guinea limestone are exposed. See the folds. You can see the big valley up along the side here, which is a big strike slip fault zone that is coming up and through here. Then we also have these amazing roads that Benjamin Suppi did the famous study on the heat road coming up through the top. Basically, what I'm trying to say here is that we understand tremendous amount about the geology in the vicinity, while many other deposits, you can get it located, but the issue of the surrounding geology is not so well understood. And it was by studying this that we came to a big understanding that this had a very, very interesting tectonics story. Okay, in terms of deposits of the world, here is a diagram from, oh gosh, almost 25 years ago now. It's a triangular diagram. And if you look at it, the axis over here is gold, over here is molybdenum, and of course up here is copper. And all the dots are deposits around the world. But the stars are the giant deposits, the top 25 deposits in terms of copper and in terms of gold. The issue of the top 25 deposits, copper, molybdenum, gold, in terms of their economics. And you can see most of the stars are either on this line here, which is the copper gold axis, or on this line here, which is the copper molybdenum axis. And when you look close at the tonnages that we've got here, there are some deposits, they got a lot more molybdenum than copper. Most of them are up here with the copper and the molybdenum together, but there's a much more spectrum. There's a much more of a range here for the copper gold systems that's out through there. And then there's some that are in the middle, but most deposits are along either one of these axes here. You can say they're copper gold or copper molybdenum in terms of their dominant metals, in terms of the economics. And then here's some of the names to go with the deposits. You can see the names of the deposits. Many of them will be familiar to you. Lo and behold, here's Grasberg. In terms of its economics, about halfway up the line here between the copper and the gold, in terms of what copper gold weight percent gold, copper and weight percent gold in grams per ton. It's almost a 50-50. 1-to-1 kind of ratio is what they refer to it here. Then here's a whole set of the copper molybdenum deposits that are up and through here. Most of these are in South America or Western North America that you can see here. While the ones on the copper gold ones are spread around the world, but quite a few of them are in the Western Pacific that's here. There's a few notable ones that plot kind of in the middle. One of them is in Iran, Sar Shemesh. And then here's Bingham, which is the United States' biggest deposit, though the new mine in Arizona, Resolution, is also quite large, but it's not on this diagram here. So I hope everyone has the picture here of that most deposits are on one side or the other, and what could this be due to? Let's look at the map around the world, and what I have done here is located them, and you can see of the major giant deposits: Western South America, Western United States. There's lots of small little guys, but the issue is the big ones that are active mines and all. Most of them are marked in through here. The issue is what's the age of the deposits on this plot. And as you can see, the ones in yellow are pre-Cenozoic, but almost all the other ones are of Cenozoic age. The issue is in the last 60 million years is where most of these deposits have formed. And that's a very interesting observation. I think the simple explanation for it is if they're really young and they form shallow, well, they can still be preserved. If they are old and they formed within 1 or 2 kilometers of the surface, there's much more likelihood that they've been destroyed by erosion. So that aspect about deposits, I think we have a pretty good understanding of. But again, the association with subduction zones is quite apparent here for quite a few of these here. Western North America, Western South America, the association with the subduction in the last 100 million years is quite evident. And then we get these other deposits that are scattered, which, Cadia in Australia, that's far from a subduction zone today, but it was back in its time. Oyu-Tolgoi, part of the collisional tectonics to create parts of Asia. Over here for Shemesh, Iran, These are all ones where it's not just a regular subduction zone. So there's some of our hints of the tectonics of a different setting, but convergent margin related. Here's a figure that's been repeated in many papers that are out there, the issue of the subduction zone diagram. The association of porphyry copper deposits with subduction zones, well, that's what you're going to see in most textbooks. You get the plates converging, and back in the beginning days of plate tectonics, 1972, Silito, and several others pointed out the association of subduction zones for making porphyry copper deposits. So the basic picture of a diagram like this is fairly simple. There's the oceanic lithosphere going down the subduction zone. The idea that at depth of about 100 kilometers, magmas are being generated. These magmas rise. The likelihood that they're going to pool in the lower crust if it's in the crust, but that there'd be some shallower level magma chambers, which are basically underneath the volcanoes, subvolcanic chambers, but large magma chambers, batholithic scale magma chambers, quite common that's out there. The association of subduction and porphyry copper mineralization is well established. Now, the details of what's going on is where the debate is. The details of what's going on is, why are the magmas here? Well, in a subduction zone, the number one reason for making magma is brought down to depths, and at about 100 kilometers, enough water is present, added to the hot mantle, the asthenosphere, that partial melting occurs, and we make basaltic magmas that are wet. They rise towards the surface. These water-bearing basaltic magmas can pool in magma chambers and interact with the lower crust, rise up, and eventually feed the volcanoes. So we really have two types of subduction zone arcs, volcanic arcs, ones which are made into continental crust and ones that are made in organic crust. And I think you can tell by looking around the world right now, quite a few of the deposits of the world are ones that were actually built into continental crust. So that's one of our topics that's of considerable interest, is what's the role of the continental crust in terms of affecting the behavior of the magmas. Certainly the chemistry of these batholiths, associated volcanics that we have there, have been perturbed by interacting with the crust. They have assimilated the crust. There's been fractional crystallization. The magmas evolved that come out at the surface are very different than what they started at deep down here. But along the way, they end up becoming ones that potentially become mineralizers. But the real observation is most don't, only some do. And that's the puzzle, which I tried to address last time, is that you got to have the right structural setting, you got to have the, which is the plumbing, and you got to have the right cooling history to get the fluids coming out deep down. And the presentation last time dealt with that. I'm much more concerned here today about making the magmas and the interactions that are happening down here. The issue of what's going down the subduction zone as a contributor to the magma, the interactions happening in the lower crust, and what might happen along the pathway as it heads up to the surface. But I think most people, if you ask, well, how do we make porphyry deposits, they would point to a diagram something like this, where subducting oceanic lithosphere gets down to about 100 kilometers, magmas are generated, and then some kind of interactions happen in the crust, and all that combine to make, some can make ore bodies, many do not. Now, going back 20 years, year 2000, the issue of, well, wait a minute, it actually became the great focus in porphyry coppers. What was the reason for sort of a change in the focus? The change in the focus was the economics. The economics of having a deposit with copper and molybdenum, well, that's good, but sometimes when things are more difficult, having gold is excellent to have as your associated metal. And really the big trigger of this was the realization of Grasberg. The discovery of Grasberg in 1989, by 1992, 93, it became apparent it was a supergiant deposit, one of the greatest deposits on the world. And it not just was a great copper deposit, but it's actually the world's largest accumulation of gold. So you got both metals, and that made the economics of the Erzberg-Grasberg district to be so spectacular, and obviously a major contributor to the economy of Indonesia and a major source, about 5% of the world's copper supply. So the issue is, by year 2000, trying to find the next Grasberg became the subject. You know, the part of the story, of course, for Grasberg is the company Freeport had been there for almost 20 years before they realized the elephant was 2 kilometers away from the original Erzberg and the associated skarns. The idea that the tonnages can be so big. Well, one of the first compilations out there to try to address this, Mueller and Groves, but other people did it too, was the realization that these magmas associated with Grasberg and other copper gold deposits are actually a little odd in their chemistry. The most distinctive aspect about their chemistry being different is that they're higher than normal potassium content, potassic magmas. And so that actually guided a lot of exploration efforts, was to try to find these potassic magmas, often described as being lamprofers or being described as being shosonites. The idea that, oh, if we got socionitic magmas, it's more likely we can have a copper gold deposit than a copper molybdenum deposit, and many people were trying to hunt for that. The other one was the tectonic setting of these types of things where we have potassic magmas. This goes back before the realization Grasberg was one of these things, but the issue of, well, where do we get socionitic magmas? They're related to collisional tectonism, late in collisional tectonism. And this idea that, well, it's subduction related, but it's a bit different. It's actual collisional tectonism may be fundamental. Started to become apparent in our work, obviously in New Guinea, had come to that exact conclusion. And we'll work our way through that as we continue on here. Now, how can it be related to collision? In the early 1990s, when I was working in Erzberg-Grasberg area, I was completely content to say, okay, it's after the collision has happened. Well, let's look at this diagram, which is the thinking that existed up until the mid-1990s for what happened in New Guinea. Here was Northern Australia. Here was a down to the north subduction zone, intraoceanic subduction zone. We got the Australian plate with its oceanic end going down to the northeast, subducting away during the Cenozoic until a collision happened. And at this collision made most of the island of New Guinea. And in so doing, we jammed up the subduction zone. And in the early 1990s, this was the diagram that most people thought was the case, is we jammed up the north dipping subduction zone and it broke through on the north side and became a southwest dipping subduction zone. And that the magmas in the highlands of New Guinea was from the southwest dipping subduction. In other words, it was subduction, the same basic story, except it changed direction, flipped, subduction reversal. Oh, it seemed like such a good story. Now let's look at this a little bit more in terms of the tectonics of these copper gold deposits. Here's a plot from David Cook's magnificent summary paper in 2005, where he lined up the giant copper deposits of the world and the giant gold deposits of the world. And lo and behold, you can see some of them, El Tiente and Chuquicamata, have enormous gold, but their byproduct metal is molybdenum. You have to go to things like Grasberg that has gold that's high in copper and also high in gold. There's Bingham, which is another one that has got both. Bingham's also got a noticeable amount of molybdenum. But a couple of the other distinctive ones that appeared was Oyu Tolgoi, that great discovery in the late 1990s, Oyu Tolgoi, and then Shar Shemesh for Iran. That these were deposits which actually are not so obviously directly steady state subduction. And it became apparent that the collision story was part of it. And so here's my compilation of re-looking at this, where I said, okay, let's divide the world in giant deposits from copper and molybdenum, giant deposits in copper and gold. Here's a list of all the giant copper molybdenum deposits. Over here is the giant gold with copper deposits. Here's giant copper plus gold. Ooh, there's Grasberg, Oyu Tolgoi. But the issue is over here, we've got the copper gold deposits. Over here, we got the copper molybdenum deposits. We got a couple that are in the middle here, so there's some debate. But here becomes adding in the tectonics. All the ones over here with copper and molybdenum look like they're areas with long-term, pretty much steady, but somewhat evolving subduction. Well, over here with our copper gold association, all the different deposits around the world are ones of probable collisional tectonism. And of course, some people have argued not just the collisional tectonism, but we actually directly had subduction reversal. So we're going to address that here. But here's the other distinctive aspect. These deposits with the gold, the ones shaded in yellow, are also ones that are relatively high potassium magmas. Sosenitic, lampropheric. Sosenitic is the phrase a lot of people have, high potassium andesite sometimes. But lo and behold, that potassium association is pretty distinctive. Most of these magmas are going to have 2 to 3 weight percent potassium, some 4 weight percent in potassium. The idea that they are higher than normal, far from being your normal, certainly oceanic basalts, definitely enriched in potassium compared to normal subduction zone magmatism. So this is what I take as a definite hint that something is going on in these collision-related settings that not only have the gold, but also the potassium. So here become the questions of today. Why are some porphyry copper deposits copper molybdenum settings and others are copper gold? And what I hope that you end up thinking more about as I continue the discussion here is we're talking convergent plate margins. We are talking in comparison to pretty much normal subduction zones. A normal subduction zone is one where oceanic lithosphere is going down, and if you look at it 10 million years later, or 10 million years in the past, the geometry pretty much looked the same. Some places are fast at 2 centimeters per year or 3 centimeters per year. Slow. Some places are fast at 6, 7, 8 centimeters per year. But the issue is it looks pretty much the same over time. That's very different than a collisional setting. A collisional setting is we've jammed the subduction zone, and how it looks today is very different than what it's going to look in 3 million years from now. Why? Because collisional tectonism is going on. The subduction zone is jammed. Something's got to rearrange itself. So now let's look at this issue of metal, the types of deposits, the copper, molybdenum, and gold. Copper, molybdenum, and gold. What's normal? What's normal out there in continental crust? And a lot of people have suspected that the crust is critical in these systems. My conclusion is it can make a difference, but it's not the critical thing. But let's just look at what the numbers are. Normal copper contents in continental crust are remarkably small variation. This major compilation from the world with thousands and thousands of analyses have about 27 part per million copper is what typical continental crust is. Molybdenum, on the other hand, average continental crust also doesn't vary very much. It's around 1 part per million molybdenum. So about 27 parts per million copper is typical for crust. About 1 part per million molybdenum is typical for crust. And then for gold, well, it's much more rare element. And according to Rudnick and Gao in their compilation, average continental crust is about 1 part per billion. So now we have what are normal numbers. If you just take an average piece of continental crust, analyze it away, these are the sorts of numbers that you would expect. So what do we have to have ore? Well, we got to enrich. We somehow have to take what's typical continental crust and have something happen, add magmas, make hydrothermal fluids move, but just how much has to happen? What are the enrichment factors to get what we call medium grade ore? And what medium grade ore for copper is about 5,000 parts per million. Copper, that's 0.5 weight percent. Grasberg is twice that. But the issue is compared to normal continental crust, we've got an enrichment of about 185 times. Molybdenum. Molybdenum to be ore grade is about 200 parts per million, at least to be noticeable as a co-product in your mine. That's about 0.02 weight percent, but 200 parts, oh, that means an enrichment compared to normal continental crust of about 250 times. Gold, well, a good co-product of gold in your deposit would be something like 0.4 gram per ton. Grasberg is right around 1 gram per ton, so it's more than twice this value. But that's 430 part per billion. But again, that's an enrichment factor of over 300 times. So to turn continental crust into ore, we actually have to somehow enrich. We got to have processes going on to concentrate it by a factor of 200, maybe 300 times what is just normal that's out there. So obviously an ore body is an extraordinary concentration of metal. The issue is how much of an extraordinary concentration we got to have enrichment factor processes going on. And that's largely what I was talking about last time. But what we're trying to get at here is while some of them are highly enriched in molybdenum, others are highly enriched in gold to go along with the copper. Why are some doing the molybdenum thing and why are some doing the gold? Look at regular subduction zones. Regular subduction zones, and here's a couple diagrams. I have a book coming out, and this book will have these diagrams in it. At any rate, a regular subduction zone, hey, subduction zones. One of the great discoveries of the last 25 years is realizing that subduction zones really have two end members, subduction accretion margins and subduction erosion margins. Subduction accretion margins are where we grow big accretionary prisms. Oh, that's happening off of Sumatra right now. We're also off a part of Java, but the issue is an accretionary prism at the front end of the overriding plate. So yeah, something gets subducted down to depths of about 100 kilometers, magma generation event that makes the volcanic line. But out at the front end, we're adding material by off-scraping, underplating, making an accretionary prism. Some very interesting geology, of course. But the conveyor belt's bringing material in here, and some of that material gets dragged down to great depths to become melted, to become part of the volcanic arc system. But a lot of it is scraped off at the front end. So this is our story of accretionary margins. And let's just thinking dynamically here, the idea that the plate is coming in, bringing seamounts and other features. But if subduction is at 7 centimeters per year, to go from the trench axis down to the depths of arc magmagenesis at 7 centimeters per year, or to go about there in 1 million years, there in 2 million years, whoop, we're down to depth of arc magmagenesis in about 3 million years. So in a good old subduction, it can be very quick, the cycling time from the surface to the depth of arc magmagenesis, and up it goes. So that's one class of subduction zone. The other class is the erosive margin. And this was a big discovery in the 1980s. The type example is the Mariana subduction zone in most people's thinking. But what's happening in an erosive margin? The overall geometry is pretty much the same, but what's actually happening is the sediment layer that's coming in is going on down to the depth of arc magmagenesis. And not just the sediment layer, some of the overriding plate is. So instead of growing an accretionary prism, we're actually scraping off the front end of the overriding plate, chewing it off, and it's subsiding and migrating inwards because of the process of subduction erosion. So in subduction erosion margin cases, instead of adding to the rock record, we're destroying the rock record. And this is a very interesting subject. Why do some subduction zones have accretion and some are dominated by erosion? Well, the key factor is how much sediment's coming into that subduction zone. And that's something I published a whole set of papers on, I'm very interested in. Before my life in ore deposits research, I was really trying to understand subduction zones. And the concept of what's happening there and deep sediment subduction, this was actually debated until the 1990s. But one of the great discoveries in the late 1980s and well confirmed by middle 1990s, subduction zones consume all of their sediment. And how do we know this? We know this because of the isotope beryllium-10. Beryllium-10 is generated by cosmic ray bombardment of nitrogen in the atmosphere. It rains out, sticks to clays. It's all over out in the ocean floor, except the half-life is very short, about 1.5 million years. And what that means is sediment that's more than 10 million years old, well, it's decayed, it's gone. But the great discovery in the 1990s was all these little yellow triangles. These are volcanoes. There's New Britain, there's Kuril Kamchatka, Western Aleutians, parts of Central America, parts of Southern South America, where lo and behold, beryllium-10 shows up in the arc volcanoes. The only way to account for this is not just some sediment went down the subduction zone, all the sediment in that subduction zone went down to the depths, because it's only the youngest sediment, the very top of the sediment pile, that contains beryllium-10. And you can see it's mostly faster subduction zones, 8-9 centimeter per year kind of convergence rates. Here we're talking about 6 or 7 centimeters per year. The slow subduction zones don't have it. Slow subduction zones like Lesser Antilles, southernmost Chile, northeast New Zealand, Hikaringi. And it turns out for most of Sumatra, is placed reports I hear, Sumatra, Java, towards Banda, we don't have beryllium-10. But many do. And the issue is, when you look close at the tectonic history of the margins, the ones with beryllium-10 are the ones that are orange color coded here mostly. And if you look at the code, those are margins with subduction erosion. So the issue is complete sediment subduction at places where we have subduction erosion seems to be the case. There's a few exceptions to this. We can talk about it later. But the issue of beryllium-10 as an indicator of complete sediment subduction, we got it. Before middle 1990s, the issue of most people thought there's always accreted sediments. That's not true. Some subduction zones consume everything that's coming. So here's a diagram that I put together to think about what's going on conveyor belt, subduction conveyor belt that's coming in. In a margin with subduction accretion, we have material that's being conveyor belted in the oceanic pelagics. They're coming in from the oceanic regime. They're getting blanketed by sediment that's coming in from the arc continent regime. And if we have a big thick pile of sediment that's coming in, thick pile being say 500 meters, maybe 1 or 2 kilometers, but some of it gets knocked off, it's off scraping. And when it's off scraped at the front end, we grow an accretionary prism, and the young stuff cannot go down to the depth of arc magmagenesis. The issue is some of it can also be added to the overriding plate by the process of underplating. But the conveyor belt brings sediment deep down, but it's only the bottom of the pile. In a subduction erosion case on the other side, there's not much to begin with. Intraoceanic subduction zones are where this is common. We have stuff coming from the overriding plate, but not so much that it can't all be dragged down. And in here, instead of growing an accretionary prism, you can actually see the coupling of the overriding plate to the subducting sediment layer. And in so doing, it gets dragged down, brought down to the depth of arc magmagenesis. So we've really got two very different mechanical behaviors of regular subduction zones. But in both cases, we're bringing sediment, which has water in it, down to the depth of arc magmagenesis, adds water to the mantle, water flux melting, and we can make explosive volcanoes. So, thinking about the sediment that's coming into a regular subduction zone. The sediment, we have the trench axis deposits. That's the stuff coming from the overriding plate, often highly volcanogenic, channelized in mass flows. Oh, okay. That's the stuff that's coming right now into the trench, can go down the subduction zone. We also have the hemipelagic sediment. This is the blanket of material that goes oceanward from the trench axis. It's usually very small particles, but it rains out of the hemipelagics. And then we have the true pelagics. Those are the parts of maybe 50% of the ocean floor. It's mostly pelagic sediment. The accumulation's up to about 200 meters thick, but this is just the slow rain of sediment coming down on the seafloor. And then at the very bottom of the pile, we have the near ridge pelagics, which often are rather metalliferous. These are the basal tens of meters of sediment. They're metalliferous, raining out of the ocean floor. Some of them are direct hydrothermal precipitates from the hot fluids at the ocean ridges. Others are, the most famous example are the manganese nodules, the hydrogenous precipitates. These are metal-rich, precipitated directly from seawater. So the idea that we have various different types of sediment, definitely, but the bottom of the pile are these pelagics, clay-rich stuff for the most part, sometimes quite silicious, but a lot of clay component. When we start looking at these sediments in the marine clays, we can see they vary quite a bit in terms of the details of their geochemistry. But here's the most interesting thing. Your typical continental rich shale has a little bit more copper than normal, has pretty typical molybdenum and gold values, molybdenum of a few parts per million, gold of 2.5 parts per million, that these compilations indicate, oh, they're enriched a little bit, maybe 2 times normal continental crust. But continental shales, which huge volumes of them are out there, nothing particularly special. But the pelagic clays, when you start looking close, these are very interesting. The pelagic clays, quite commonly enriched in copper, and in fact, manganese nodules, that's why some people want to mine them from the seafloor. 4,500 parts per million copper. But look at the molybdenum values, hundreds of parts per million molybdenum. And so the issue is the seafloor pelagics are enriched in copper, enriched in molybdenum, and there unfortunately is not much data. Maybe someone knows of some papers I don't know about, but the gold values are not particularly special. So they got high molybdenum to gold ratios as best as I can tell from compiling the literature on the subject. So oceanic pelagics, the bottom of the pile, are enriched. They're enriched in molybdenum by a factor of at least 10. They're quite commonly also enriched in molybdenum by a factor of more than 100. So the oceanic pelagic sediments, in terms of being a contributor to subduction zone magmatism, I think that's the key. The issue is those sediments that are going down to the depths of arc magmagenesis that are enriched in molybdenum, it contributes to it. And as a result, we can end up having these copper molybdenum systems with associated subduction zones. There just is no special addition in the primary magma of gold. So here's the little diagrams illustrating this that I made long ago with a paper with Todd House in 2008, where I tried to argue that, oh, the pelagic sediment component going down involved in arc magmagenesis. But that pelagic sediment that we have in it can end up making volcanic arcs, but close to the deposits in Western South America and also in Western North America. And I did not talk about this, but the fact of the matter is, in both Western South America and Western North America, we have multiple deposits, many dozens of deposits in both continents, but the subduction has been going on pretty much continuously for more than 200 million years. Yet we only have bursts of activity when mineral deposits happen. In the case of Arizona, most of those porphyry copper deposits are about 40 to 60 million years. In Western South America, we can a little more directly see what it is, but in both cases, the mineralization is associated with flattening, episodes of flattening of subduction. And I think this is very, very, very important. The flattening of subduction changes the position of volcanic arc and sets up an entirely new environment in terms of temperature conditions. We're not going to have time to get into the details of this, but this, I think, is the other special ingredient for making porphyry-type deposits. You got to have the right chemistry, you got to have the right plumbing, but you also have the right thermal conditions, and changing from steady state subduction to a change in subduction by changing the plate dip is very important. And we talked about that in that paper. So the enrichment of these things in molybdenum as the sedimentary component for copper gold mineralization in steady normal subduction zones, steadily convergent subduction zones, mineralization descending plate dip, that is copper molybdenum systems of the world. And I think you can see, here's the map of the world where most of these copper molybdenum systems are. We have quite a few in Western British Columbia and all, but they tend to be pretty small guys. Is that overall associated with subduction, changes in subduction that's there. So I think we have got the diagnostics on that. Now here's where, coming back to the wonderland of New Guinea, the Ertsberg-Grasberg district gives us insights in terms of this other style of convergent margin magmatism, collisional magmatism, and that's what we're going to look at here now. The idea that Ertsberg-Grasberg district is a special place, not just because of the deposits, but because the geology is so good to tell us a story. This bathymetry map shows it quite nice. There is the collision mountain belt in red, the collisional tectonism of Australia entering the subduction zone, the north leading edge of Australia plugging up the subduction zone. pushing up the big mountain belt, it's just so obvious. This is not a steady state subduction zone. It's a collisional subduction zone. And the issue is when that collision happened, the deformation associated with it set the stage for Grasberg district. And obviously in New Guinea, we have IAGI, free river, set of other deposits in it, also a fertile ground for exploration in West New Guinea. But story of the tectonics of New Guinea, it's quite evident in this basic bathymetric map that we see here. The issue is it's collisional tectonism. And that's what we want to look at more closely. Here is the island of New Guinea. And we talked a little last time, but just to get everyone thinking a little more about it, it's shaped like a bird. There's the bird's head. There's the bird's neck. There's the bird's feet. There's the bird's tail. It's more than 1,000 kilometers long in strike distance. The north coast of the island is largely the oceanic arc complex, which has been pushed up and largely buried by debris coming from this great mountain belt here. The great mountain belt of the Central Range has on the north side the ophiolite, the Irian ophiolite. Down over here, the Papuan ophiolite, two of the great ophiolites of the world, slabs of ocean crust. It's the basement of the forearc terrain, tilted up on in. Here in blue is the metamorphic belt. That is Australian passive margin sediments for the most part that have been gone down the subduction zone, been metamorphosed, highly deformed. Oh, there's no great accretionary complex. This was an oceanic arc complex before the collision happened. Oceanic arc complex similar to the Mariana subduction zone. But this stuff being bulldozed against it, caught up in the collisional tectonism. And then on this part here in white is with the lines representing the fold and thrust belt of the passive margin sequence of Australia that's been bulldozed up. This is the host rock for the ore deposits of the Erzberg Jurassic District. It's the host rock for Octedi and Frieda River and other things that we've got going on in the PNG end of things. But the issue of the Erzberg mining district, it's in this location right through here. Now, the island of New Guinea on the south side, it's mostly an island, it's really a swamp. It's just the sediment that's eroded off this mountain belt going to the south, fills it in. Sediment eroded to the north, fills in the forearc, fills in the around the arc volcanoes, so they're very poorly exposed. But the first order tectonics for almost 1,500 kilometer strike distance, the collision. Now, here is what got my attention at the beginning of working there. When I first went to New Guinea and Freeport had its great exploration program, I thought this was actually quite amazing. Quite amazing because at the time people thought that the magma in the highlands was because of subduction reversal. And here's where the New Guinea Trench is. It's a bathymetric depression on the north coast of the island. The idea was subduction had flipped, as I showed in a diagram ways back. Flipped and gone down to 100 kilometers, and now the new magmas are coming up to make it. But what mystified me, I thought was strange, was why did the new magmas know to come up in the very highest part of the mountain belt? And in the case of Erzberg-Grasberg, they're right next to the highest peak of all. I thought this is really quite fortuitous. If this is from a subduction zone down to the south, how did it know to make the magma right underneath the highest part of the mountain belt? I thought that was very strange. The other thing about the deposits on the eastern side of the island, there's Octedi right near the international border. There's another significant gold deposit, Porphyry. There's Frieda River. But the volcanism that we've got. The volcanism on the east side of the island, well, actually the little black triangles are still where the volcanoes can be seen. It's just turned off. We got Pliocene volcanism on the east side of the island. The west side of the island, where the Freeport exploration geologists like Wayu Senyoto and Sugang spent so much time trying to find another Grasberg. The issue of, well, we just got little patches of magmatism. I believe actually the volcanism was a lot like what's over here, but it was a blanket which has already been eroded off. But somehow the magma's popped up along the spine and on the PNG side doing the same thing. This, I thought, was a very, very fortuitous relationship. And it wasn't until the mid-1990s that I finally realized it's not from subduction from the south. It's because of the collisional magmatism. So here is what people thought before. fact, here's the diagram from 1976, down to the North Subduction. Here is the collision of Australia jamming the subduction zone. The plate, disappearing because now it breaks through on the north side and we have a new subduction zone. This is what I thought was really quite remarkable for it to know. The other part of the process, why did the volcanism stop in West New Guinea? It's pretty much stopped in Papua New Guinea, but why did it stop on the Papua side of Indonesia, or the old Irian Jaya side? I thought that was very curious. Why did it start, have a distinct event, and stop if subduction's still supposed to be going on? Well, here we're going to take the time to work through the diagrams, which we didn't do last time. But this is what I think is related to copper gold magmatism around the world, but best understood here in New Guinea. Here's our major publication. We call it Collisional Delamination in New Guinea, the Geotectonics of Subducting Slab Breakoff. How did the magmas form? Hey, here's Grasberg in 1991 when they're first starting to mine the top of it. But here in the great picture of the top from a helicopter, you can see the folds of the New Guinea limestone group. There's gigantic kilometer scale folds. And over here is a syncline you can see coming up and through here, the Yellow Valley syncline, headed right towards Grasberg. Off in the distance, you can see some more synclines and anticlines. This is the collision-related folding and faulting. Superimposed upon it is the intrusive activity, as well as, if you look close here, right down this valley is the Marin Valley fault zone. Right down this valley and coming out through that notch is another stress of fault. Postdates the collisional deformation. So, how did this all come to be? Here is the regional map, the collision across the island of New Guinea. Well, it sort of zippered its way from the west to the east. And what we're going to do is look at a set of cross sections. As the collision happened, the magmatism was more active in the west between 4 to 7, 8 million years ago, and really started up with the oldest stuff at Porphyry, but really started 5 to 1 million years ago in the islands of East New Guinea. So that needs an explanation too. Why did it change from west to east? So let's look at this in terms of the tectonic story. The tectonic story is there's Australia with an oceanic end of the Australian plate going down to subduction zone. Just doing perfectly good. 25 million years ago, steady state subduction. Looked a lot like the Mariana subduction zone of today. At 12 million years ago, those limestones tell us they're starting to become deformed. The youngest limestones are about 12 million years. The bulldozing of the passive margin sequence. We actually know that it was simply steady subduction until about 12 million years ago, and then it starts to pop above the sea, looking a lot like the area of Timor does today. It's popping above the sea, starting to shed sediment, but subduction is still continuing. Here we go to 8 million years ago. We now have the issue of the collision is beginning. The collision is beginning. We now have the tectonic story of, it wants to jam the subduction zone, and what happens next? And so this is where the thinking was evolving of how does a plate break? And the concept of delamination goes before this. The idea that we can peel off oceanic or lithospheric mantle because it's more dense. This is the concept of delamination according to Peter Bird. He also had the picture that you can peel it off, heat up the crust, and have a magma event. But this is the paper that got my attention in 1990. And here's the diagrams. How do you actually jam a subduction zone? Well, we have the plate come in, and then it rifts apart. Rifts apart by faulting, rifts apart by ductile stretching, simple shear, pier shear. Those interested in rifting tectonics are, I'm sure, well aware of the argument. But the idea that this process is fundamentally important for breaking the plate apart. But in so doing, the asthenospheric mantle, AM, upwells. It upwells into the gap, decompresses, and it melts. Here's a 1995 paper. The picture is we jam the subduction zone and we have slab breakoff. Same process of upwelling asthenosphere, magma generation to rise up into the orogenic belt. So calling it delamination, pulling apart, calling it slab breakoff, all part of the same words to describe the overall process, but we think we know the details here. Now, I'd have to think about some of the processes. The crust and its coupling to the mantle. There's a big difference between oceanic crust and continental crust. Oceanic crust is well coupled to its mantle roots, while continental crust can get pushed off. The concept of lithospheric buoyancy, negative buoyancy, positive buoyancy, neutral buoyancy. Well, oceanic crust cap lithosphere is negatively buoyant. There's a slab pull force to pull the plate deeper into the earth. Positively buoyant plate, though, like the continent, it doesn't want to go down. It survives for billions of years. It obviously resists subduction, positively buoyant. Then another part of the story is, where is the strength of the plate? Is the plate the same strength everywhere? How is that slab pull force transmitted? And the answer is no. The top of the plate is cold and strong. The deeper part of the plate is weak and ductile. So let's look at how we think the collision process evolved here in New Guinea. The idea that the edge of the Australian plate that was thinned out to maybe 25 kilometers thick continental crust partially went down the subduction zone, but in so doing jammed it up to make the Great Central Range of New Guinea. The density structure of oceanic crust cap lithosphere versus continental crust lithosphere is illustrated in this diagram. When it's oceanic crust lithosphere, it's thin and it's more dense. When it's continent crust lithosphere, cap lithosphere, it's lower dense and thicker. This resists subduction. This can go down no problem at all. So there's our density profile. So this whole idea of oceanic crust cap lithosphere being inherently subductible, definitely. Part of it's related to the temperature structure, but that's another detail we'll deal with some other day. So if we start looking at this, the ocean crust cap end of the Australian plate, that can subduct no problem at all. The thick part of Australia you walk around today, that's positively buoyant. It's thick and low density. But somewhere out there in the continental shelf is where the shift happens. The shift happens from negative buoyancy to positive buoyancy. And according to my analysis, it's somewhere between 15 to 25 kilometers, maybe 15 to 20 kilometers, 17 kilometers is a nice number. But a thickness of crust, continental crust on top of lithosphere, it's actually can prevent it from going down. The other part is the coupling of the crust to the mantle. When it's thin crust, it's well welded. When it's thicker crust, it's ductile enough that it can be shoved forward. The concept of the strength of the lithosphere is the peak strength at the top, is the peak strength at the bottom. No, it's down there at about 15, 20 kilometers. Up near the surface, the confining pressures are lower, it's cold. Deep down, the temperatures are high to make it ductile, so that the peak or the push and the pull force is not transmitted anywhere. It's the upper 10 to 20 kilometers of the plate. So now we have a bunch of concepts to think about how the plate will break. So here we are. We're going to go through this set of cross sections based on the reconstruction of what happened in New Guinea, but I'm quite confident that this is close to the story. 25 million years ago, we had a down to the north oceanic subduction zone, much like the Mariana subduction zone of today. An oceanic overriding plate, oceanic lithosphere of Jurassic age going down to subduction zone. But as you head to the south, you get to the Australian continental margin. You head far enough to the south and you got thicker continental crust. You head far enough south, you got Australia. But here's the position of where Tamika is. Those of you who've been to the mining district would have landed at Tamika. So that helps put it in perspective of what's going on here. Here's our scale, 100 kilometers. 100, 200, 300, 400, 500, 600, 700, 800. In other words, we got a couple thousand kilometers between Tamika and the oceanic arc complex at 25 million years ago. These little boxes schematically show the displacement, which the plate motion reconstruction indicates was converging at about 50 kilometers per million years. So every million years, is the width of this gray box is the amount of translation that was happening. So here we are. We move forward to 10 million years ago. By point in time, all the ocean plate has gone down the subduction zone. At 10 million years ago, the edge of the Australian margins entered the subduction zone. Here's the Uranophilide belt. Here's north coast of New Guinea. But what's going on here is we're bulldozing the continental margin. That's those big folds that we're seeing up at the top of the mountain. Folds and faults, they're getting involved in deformation. There's where Tamika's location is, still under the shallow sea. But at this point is about when positively buoyant lithosphere wants to turn the corner to go down the subduction zone and the true collision begins. At this point, we're just scraping off the sediment pile. The crust is going down. But at 8 million years ago, problems are happening. 8 million years ago, those problems are bulldozing more sediment, but at this point, trying to turn the corner of positively buoyant Australian lithosphere, it's at the corner. It's really jamming things up here because it doesn't want to go. So what's the first response? The first response is the slab of continental crust starts to get, I call it, it's getting decapitated. We're pushing forward a big block of continental crust. It's forming a gigantic fold. Why is this happening? Because the peak strength is concentrated in the upper continental crust here. This is the peak strength diagram. There's the fracture strength. There's the flow strength. Depends exactly the condition, somewhere between 20 kilometers. That's where the pushing effects from the incoming Australian crust is translated into the subduction zone. Also, that's where the pull effects from the oceanic end going down are transmitted up dip.
Gambarnya nggak usah keluar ya. Ini gambar aku bisa nggak gambar ini bisa ya.
Is that the question? Oh, keep going. Okay, so the issue here is, okay?
Okay, Pak, keep going.
Okay, keep going, because we're gonna, it's like a movie now. We're gonna move through time. So the issue of the collision and the positive buoyancy, William doesn't want to go down. Tamika doesn't want to go down the subduction zone. The issue of we are now piling stuff up because of this, but it's causing all kinds of interesting things to happen underneath it. And here's what's going on at 6 million years ago. Here's Tamika. Here's the Uranophilide belt. There's the coast of the island. Well, we jammed the subduction zone, but we got a crust formation. The giant Mapunduma anticline is forming. We've got the folding and faulting, but much more important, this end is moving at the speed of 50 kilometers per million years. The plate is pulling apart. And if you look close how the plate pulls apart, the top part's going on down, just translating here, but we've got a big tongue that's pulled out. A big tongue of lithospheric mantle, the upper part that's strong. This part here used to be near that part there. That part there used to be near that part there. This part here used to be down there because this is pulled out as a tongue of strong plate. This pivots up. Oh my gosh, this all happened fast. In 2 million years, all of a sudden, all of this, which used to be lithospheric mantle, is now a asthenosphere. It is decompressed. But the asthenosphere is already in a condition where it's ready to melt. It's really going to melt, and that's what all the red lines are here. So those are going up. The other part of the story is the lower lithospheric mantle that's stretched out, pulled up, is also getting heated by these intrusions, but also decompressing and melting a little bit. All of this is producing the red stuff here, the magma. We are having a magma generation event. And under a collisional setting, particularly one that's happening at these kind of speeds, it happens very, very quickly. The plate pulls apart, magma is generated, not because of down to the south subduction, but by ripping the plate apart, and it's coming up underneath the deformed continental crust. Here's my diagram to try to illustrate it in 3 dimensions. Here's the subducting plate. There's the overriding plate, the subducting plate pulling apart. And the issue is that if you take a plate and you want to tear it apart, does it just all instantly tear? And the answer is no. It's like a piece of paper. Do you tear the entire piece of paper at one time? No, it starts from one side, goes to the other. And there's the north arrow there. The tear under New Guinea went from the west side of the island to the east side of the island. And in so doing, we tore it apart underneath the collisional mountain belt of folding and faulting that also involves some basement deformation. And then we have the upwelling of the asthenosphere underneath it. This is the basic explanation for the magma event on the west side of the island starting at about 8 million years ago, got to the middle of the island at about 4 million years ago, and is younger on the east side of the island under Papua New Guinea. It's a propagating tear, is what I tried to show here. So there's from our paper. You can see the diagram there sometime if you want. So what we've got is collisional delamination. The subterranean plate rifting process causes a very short-lived magmatic event, but it's making a hydrous oxidized chlorine-bearing alkaline potassic magma. And why? Why is it doing that? It's because it involves lithospheric mantle. This is very important. Remember, in a regular subduction zone, it's subducted sediment, but here it's lithospheric mantle that's involved in the melting. That mantle, which is shaded in the green in the last diagram, has been fertilized over geological time, has been fertilized by stuff coming up from underneath it. Small amounts of melting in the sphere. Oh, older subduction zones that bring melts that's down there. Could be little fluids that are migrating around in the asthenosphere. It gets parked in the deeper part. And the process is called mantle metasomatism. We can have melts or fluids that dike or vein up into the lower parts of the lithospheric mantle that fertilize it over geologic time. This stuff has been studied by a lot of people, the agents of fertilization. It's rich in water, potassium, rubidium, cesium, barium, strontium, lead, boron, uranium. At any rate, these are for fluids. We can also have subduction zone magmas that do it. We can also have partial melts in the asthenosphere, which is going to bring in the potassium. There's our main potassic magma component. And in some cases, we can do it with carbonatitic magmas, carbonatitic melts that percolate up in various places. I don't think this had anything to do with New Guinea, but in other collisional settings, I think it's important. So we have various ways of adding interesting elements to the lithospheric mantle. Many studies have shown there's two types of mantle metasomatism, Marid sweet or Rip sweet, but they have in common potassium, different amounts of iron, titanium, brings in sulfur, but these are elements that get added, which can be released by a later melting event. And that's what the green is so important for in this diagram, because this is the added component in collision magmas. So those collisional magmas, where do they come from? Most of the magma is coming from asthenospheric magma, but some of it's coming from lithospheric magma, lithospheric mantle, some of it's coming from the crust. Overall, I don't think the crust helps much, but in terms of adding potassium and adding gold, lithospheric mantle, I think it's important. In West New Guinea, we've done a lot of work on this. That's an entire topic itself, but we can trace this with neodymium, strontium, and lead isotopes. And it looks like a few percent of the magmas are from lithospheric mantle, maybe half the magmas from the lower crust, about half the magmas from the asthenosphere. Much more is coming out on that in the next year or two. But now we have the issue is the gold. And is the gold really increased in the lithospheric mantle? Average mantle is about 1 part per billion. And there's quite a few places where people study this. Now, and there's more and more data coming out, but there's multiple sites where people study the xenoliths closely. And the issue with the xenoliths of average mantle, 1 part per billion, seems to be a common number. But some places it's higher. In some places, lithospheric mantle has been enriched. And there's a major xenolith study in East China, anywhere up to 15 parts per billion gold. In metasomatized samples in France, 10 up to part per billion gold. In Germany, they have found cases where they've got a few parts per billion. Xenoliths in Kamchatka, they've got multiple samples in excess of 10 parts per billion. So the issue is the lithospheric mantle enriched in gold? The answer is sometimes. Enrichments of 10 to 20 parts per million, in other words, a 10 to 20 type of enrichment of gold is reported in multiple, not everywhere, but multiple places it's been found. And I suspect there's more studies in the last 10 years that have found even more evidence for this. It's enriched in gold, but no sign that molybdenum is doing much. And then there's a few places where it's quite clearly a big effect. These are the lamprofers, which Muller and Groves talked about. They've actually got about 5 different localities where more than 10 part per million gold. And they've actually got some which are 100 part per million less, and there's the highest number of all that they report, 523 part per billion gold. So sometimes it's a lot more than 10 parts per billion. And then the Roman province of Italy, where there's been quite a bit of work, where they actually have about a third of the samples of mantle nodules are more than 10 parts per million. 16 samples out of 100, out of 200 are 50 part per billion gold. So my stance is some places clearly gold enrichment's happening. And I suspect that factor enrichment in gold and lithospheric mantle is probably fairly common. But no doubt about it, when you get potassic magma, collision-related potassic magmas, 10 to 30 part per million gold is not uncommon. So, is that enough to make an ore body by itself? No, but the same with copper. If you've got chlorine complexes going on, we can enrich the fluids in copper and gold, and from that, work our way up, like we talked about last time, to making copper-gold ore bodies. So this is the key aspect about our story in West New Guinea. By 4 million years ago, the plate's broken off, the magma generation event is over. Magma is pooled in the lower crust, but some of it bleeds up to the surface. And the question is, how did it do that? Well, again, Erzberg-Grasberg district, we understand quite a bit. We have a picture of a lower crustal magma chamber, an upper crustal magma chamber, probably at the contact between the sedimentary cover and the crystalline basement at about 10 kilometers down. Various pathways for the magma to come on up to the surface, making the Grasberg, for example, here, Erzberg Pluton there, but various places where it's coming up towards the surface. How to concentrate the metals, we talked about this last time, but you need the bubbling stock. You need sidewall bubbling deep down, more than 5 or 6 kilometers. We can make the copper-rich fluids. In the case of normal subduction zones, copper plus molybdenum fluids, collisional magmas, copper gold fluids, and then we got our fluid charged magma chamber. But how to get this geometry? Well, we dealt with that last time. We understand a lot about how to create it by looking at places like the Erzberg-Grasberg district. This is where Bunsuppi did his famous study on the heat road and discovered these grooves in the hillside correspond to strike slip fault zones, and that all the ore deposits of the district are within a strike slip corridor. The famous heat road, some of you have visited, the strike slip faults start popping out about here in the valley along the road, but all the ore deposits are in it. Here's one of the famous pictures. There's the horizontal lines. It strikes the faulting, northwest trending. And there's multiple zones of this going on in through here. And in fact, there's about a 4-kilometer wide corridor in the Erzberg district. Now we've got the strike slip faults, which are fundamentally important to make pathways for magma ascent, but also all the ore bodies are in that corridor. Here's the cross section. We can see the extreme relief here, but the strike slip fault zones along which pull apart structures. And here's Ben Suppy's paper. Multiple papers have now come out as to why this is important, but the issue is strike slip faulting, making pathways. And in this district, it happened from about 4 to 2 million years ago. The issue is having the strike slip activity concurrent with the stock. Well, the strike slip activity allows making the stock, but also draining of the cupola if the faulting is going on. And I think that's fundamentally important, as we talked about last time. The schematic diagram of, here's our fluid charged cupola near a step in a strike slip fault zone, and periodically draining the fluids to come on up to the top. Again, we dealt with that last time, but this is the diagram showing the ore bodies of the district. In green, there's Grasberg itself, But all of them, I don't think this is an accident. It's fundamentally important. The strike-slip component of the tectonics to get the plumbing. So here we are coming to an end, but the issue of the diagram, the 3D block diagram for the Erzberg-Grasberg district, I think really looks something like this. Let's review the tectonic story. Step one is the collisional tectonism to make the folding and faulting. Step two is the break off of the plate, and the thin skin deformation making the folding, but that is the magma generation down below, which then rises along these pathways, strike slip fault related pathways, pool in the lower crust near the moho, pool in the middle crust, and then bleed up to the surface in various spots where we've got tall stalks and cupolas. And where we got a tall stock going underneath igneous rocks, we have porphyry style mineralization, or we got a tall stock coming up but not making it to anywhere near the surface, but bleeding as fluids into carbonate rocks. Oh, we can make porphyry bodies. And where those fluids come up underneath, like the Erzberg intrusion, we have the Porphyry-Type mineralization in the Erzberg intrusion. So I think it all comes together. The idea that the economic geology, these economic porphyry copper, where the metal-rich fluids are under a cupola that's at the top of a tall stock that's cooling with the strikes of faulting episodically, I think it's important. That's the throttling cupola concept. And to have this combination is why these gigantic deposits are rare. So to sum up, the porphyry-type copper molybdenum systems, I think they mostly form at normal but evolving subduction zones. The primary magmas from the water flux melting of the asthenosphere, and the high molybdenum to gold ratio comes from the oceanic sediment component. The porphyry-type copper gold ore systems are mostly collision settings, decompression melting of the asthenosphere. This gold enrichment is from melting the lithospheric mantle. Overall, you get a copper molybdenum things. In both cases, the primary copper contents of the magmas are probably only about 50 parts per million, but it's the enrichment factors that are going on by the hydrothermal system. So the dichotomy is explained. It's convergent related magmatism, but one is normal subduction, but evolving. The other is collisional related. So, terima kasih. Thank you so much. And good luck with explorasi.
Thank you very much.
Thank you, Mr. Mark. Maybe Pak Arif will be moderator for our discussion.
Okay, thank you, Mbak Ochat. Thank you, Professor MarkCloos, for the excellent presentation today. So, ladies and gentlemen, we going into question and answer session. Too much thing that we got to today in this morning from Professor Cloos to giving more going into insight of the matter we discussed. We start to going into question and answer, or maybe comment. It doesn't matter. So we started from that. I see from the chatting room. We see the question from the first from Audi, I think.
Excellent.
Audi asking about, so maybe you can ask directly. Audi, can you unmute your speaker?
Very clearly, Pak Idrus.
Okay, just go on.
Okay. Morning, Prof. Nice talk. Thank you for your presentation, and always interested to see your presentation. I want to ask some question. My first question is, Richard in 2005 and 2009 explained that copper-rich porphyry are formed in the first stage magmatism, whereas gold-rich residue live at the base of lower crust, which is first magma chamber, and tend to be generated at second stage magmatism after contraction or extension. And my question is, why should it happen? Why gold live at the lower crust and tend to be generated at second stage? Why not at the first stage? Is that because of its density or something else? And my second question, I'm sorry to miss some point, but still don't get it yet. When the molybdenum commonly form, are they formed together with copper or something else? Thank you.
Okay. Yeah, excellent question. Here, I think everyone can see the slide. The issue of the stacking here. Now, this is obviously a schematic diagram designed specifically for Orangeburg-Grasberg district, but I actually believe this is very, very common for magmatism continental basement. Why do we have lower crustal magma chamber? It's basically because the density contrast, that the magmas coming out of the mantle are basalt, the primary magmas are basaltic, they rise, they're driven by buoyancy, they are driven by the pressure on them, depending upon how long the crack is, or just purely the density. And to the extent that it's the density that's driving them up, once they get continental crust, the density of basalt liquid and continental crust is generally about the same. So it doesn't want to rise much more purely because of density at that point. So there'll be the tendency to pool at the lower crust. Now I suspect at the beginning there's multiple levels of sills, but once you heat it up quite a bit with lots of intrusions, then the switch from mantle that's more dense to crust less dense, it will really tend to pool right at the moho. And depending on how much there is, will control how much assimilation you have. So that issue is related to the primary magmas are basically basalts with some water in them. The idea that there's another magma chamber higher up is related to the issue is we need to make hydrothermal fluids. And the problem is when you got confining pressures of more than 5 kilobars, and certainly at 6, 7, 8 kilobars, you will not get to water saturation if the water contents are less than 3 or 4 weight percent, which is probably the case. Up here, with a small amount of fractional crystallization of androus minerals, we can get to water saturation even down to maybe 10 kilometers depth. And that's if you want to make copper-rich fluids. The fluids, if they separate only at low pressure, less than 2 kilometers, are going to be copper poor. But at higher pressures, more like 4 kilometers, 6 kilometers, definitely at 8 kilometers, fluids will be rich in chlorine and the metal will follow. So this upper part of the system here has to exist so that we can have the copper separation in enough to make an ore body. Now, do we have to have a batholith at these depths? The answer is generally no, but for giant deposits, you need a batholith because we got to strip the metal from something that's hundreds of cubic kilometers. Certainly something like Grasberg has to have a hidden batholith underneath it. There is no evidence that the magmas making the district were more than about 50, 60 parts per million copper. So that's the logic, the perspective of why this is. Obviously, in specific systems, it can be much more different levels of chambers.
Okay. So you get the
very clear,
from,
Mark.
Okay.
Thank you for the explanation.
Good
okay,
question.
Thank you, Audi. Yeah, thank you, Mark, for the answer. And we are going into the second question from the chatting room. Yeah, I see here. From are you Renaldi? You can ask you directly to the Professor Mark.
Yes, thank you, Pak Arif.
Or not?
Yeah.
Okay.
Yeah, thank you,
Okay,
Pak.
you are there. Okay.
Yeah.
Yes.
Good evening, Prof. The question that I have for you is like, you said that the Papua New Guinea below is part of the food. So how about the Misima and the Woodlock Island is far east from the far east of the Papua New Guinea plate, Prof? What is the difference between the Lihir and Bougainville? Is it still came from the same subduction? And the second question is, Prof, how about the Kadia, Prof? Is it still associated with the reverse subduction? That's all, Prof.
Okay, I did not quite hear the second question. The reverse subduction, please repeat.
Yes, for the Kadia, Prof. Kadia in the Australia. Cadia.
Cadia.
KDI.
Yeah. Yeah. Cadia. I have never visited it, only read the papers. But with respect to that, I believe it's a similar story of collision. Though you are correct, the published papers talk about it as subduction reversal. So that is definitely what a lot of people think, how to get it related to collision. But I think it's fundamentally the plate breakoff, which is there. Now, the first question was Lahire. Oh, Lahire. That's a place I would really like to visit. Only met some of the geologists who work there. You know, that's an ore deposit that they're mining, and it's still hot. The ore is still, it's amazing, but they're mining it. Very dangerous place. I've seen the pictures of the explosions in the pit. Explosions because as they're mining, they're unloading it. But at any rate, they're still, I think they're still operating there. But at any rate, the issue of the geology there, it's very little copper. It's a gold deposit. And the issue of the source of the gold, there's been quite a bit of very interesting work that's been done there. It's looking to me like it's a story of the lithospheric mantle, enriched lithospheric mantle, which is the source of the high gold conditions they got there. But the hydrothermal system that is acting there, is it truly a porphyry type of a system or not? I do not know enough to have a conclusion. I think it might be, and that the ore body itself, the gold deposit here, is just the very top, because it's venting such hot fluid at very, very shallow depths. But it's also conceivable to me that it's actually a rather different style of magma chamber behavior. But we are dealing with fluid separation and relatively gold-rich fluids that's there. Oxidized is, again, the key thing there, so that the chlorine complexes with the gold. And then you mentioned Bougainville, a very, very interesting deposit. It's a bit older. The issue of the geology of Bougainville, another place I have not visited, Panguna deposit, was a major deposit, a lot to be that's potentially mineable. Maybe they have now got some peace so that it can be brought back to life. But it looks to me like that is a collision setting. There you have the Solomons. You have the jamming of the subduction zone associated with the Ontong Java Plateau, the plate break off. So that issue of the geology, I see the parallels to it. So I do think it's a similar story. But the full details of the subduction zone evolution in that area has another piece of complexity to it, because it's actually from the subduction from the northeast and the Ontong Java Plateau, and the breakoff looks to me like it was slower. Now the Woodlark, I think I heard you ask about the Woodlark Ridge too. Now that's a different issue. That's the breakup of the northeast corner of the Australian plate associated with the subduction going on into the New Britain Trench. And so there's a propagating spreading center that's there. So it is very close to the Panguna, but I think it's a different story there.
Okay. Okay, thank you.
Thank you, Prof.
Prof.
Thank you, Prof.
Okay.
Thank you. Good
Thank you.
question.
Yeah. Thank you, Rinaldi. So we are going into the third question, maybe from Pak Budi, Pak Ido, Mas Ido, please unmute your speaker.
Yes. Hello, Professor Marks. Thank you for the great presentations. Hey, I'm Budi. So I'm just wondering if there's an influence from the original mantle composition. Is there any influence as well from the compatibility of the molybdenum and also the gold? As I know, molybdenum is more incompatible than gold, and therefore it will be more partition to the melt than to the solid when the during the magma and the rocks when it cold. So, for example, as far as I know, island arc is more depleted in incompatible element. As we know, like the Papua, it is initially an island arc that is undergo collision during the Miocene. So, and therefore it's more depleted in incompatible element like molybdenums. Is there any relations between that with the type of porphyry deposits where some have more molybdenum and some have more gold? That's all. Thank you.
No, you
Thank you
have
for
raised a very important issue here in terms of the details of the geochemistry. The details of the geochemistry. We have the copper molybdenum types of deposits. We have the copper gold types of deposits. And we have ones which are just gold. And we have ones which are basically just molybdenum. And some people call them the porphyry molybdenum deposits. The United States has got a couple of these deposits that have a lot of molybdenum, but almost no copper. So the issue of sometimes we can concentrate these things in and move these elements quite differently from one another. Sometimes they go with the copper, but sometimes the molybdenum and sometimes the gold really take off and behave quite differently. The issue of molybdenum in a magma. There are experimental studies of various sorts that are out there that indicate, to me at least, that they are different than the way gold or copper really behaves, for the most part. Molybdenum can move as a chloride complex, but it also, under very oxidizing conditions, wants to just stay around as molybdenum as +6. +6 is an oxidation state. When it's doing that, it tends to stay in the melt as opposed to become a chloride complex and really build up and accumulate and become residual. In other words, the magma, once it's got 80–90% crystallized, the residual melt is concentrated in molybdenum. That can actually be its own mobile thing and get intruded as a molybdenum-rich intrusion, the porphyry molybdenum deposits, and be very decoupled from any previous porphyry copper type stale, because it's actually residual concentration of things under specific situations. It looks to me the higher the oxidation state, the more likely it does that, because the oxidation state of the magma. So the typical porphyry molybdenum, copper molybdenum deposits are actually less oxidized than the typical copper gold deposits, with the most obvious evidence for that, the abundance of magnetite. You get many of these porphyry copper molybdenum deposits, and they have just a little bit of magnetite, but they're there, they're clearly there. The issue is when you get a lot more of the oxidizing conditions, a lot more magnetite, then there's not so much secondary molybdenum that's there. And I think it's because it's being concentrated in the melt in that case. Sort of related to this is the gold and how it can behave so differently at times. And it's because gold can really be mobile under two very different environments. One is highly oxidizing, where it wants to move as a chloride, and the other is highly reducing conditions, where it wants to move as a bisulfide complex, an HS, gold bisulfide. In both ways, it can have extreme solubility and be highly mobilized, and then you get the right chemical environment and precipitates. That's actually a little bit of the issue with respect to Lahir, which I've just never understood enough about the geochemistry story there. It's possible that there's some other things going on there to affect the separation of whatever copper might have been there from the gold that's there. So these secondary elements have other conditions that can take over their behavior, I guess is a way of putting it, and make them behave so that they can actually end up with their own concentrations, potentially ore grade sizes and grades that's there. But your initial question was fundamentally important there, is that molybdenum is actually geochemically got a different behavior than that of copper and gold. And most cases where you got the copper molybdenum deposits, where the molybdenum kicks in its highest grades, it's clearly a little later in the mineralization sequence, more superimposed, which I think is related to its concentrating up in the primary magma before it comes out. But unfortunately, there has not been enough high pressure experimental work to show the partitioning relationship. At least maybe it's been done now and I'm just not aware. But a lot of work has been done on copper and gold. The experiments at higher have not been so much. And therefore the pressure dependence on molybdenum fractionation into hydrothermal fluids is more poorly understood.
Yeah, in terms of the tectonics, I just wondering if the island arcs are more depleted in incompatible elements, which is, it means it is more depleted in molybdenum. Well, we know like in the other side, like in Indonesia, we have Tumpang Pitu, which is, as I know, they have more molybdenums, and it's not an island arc. Is it have a difference between the initial mantle compositions that rise above from the island arcs and the continental margin settings, subductions? So if there's any relations between that and with the incompatibility of the molybdenums and the gold, maybe, just maybe, there's a relations between the tectonics and then the incompatibility of the golds and the molybdenum. That's what I think.
Yeah, well, definitely you get the right, the chemistry of the magma is important. The issue of how oxidizing it is, well, everything about porphyry copper type deposits, you got to be in the oxidizing side. If you got reducing magma, you know, they got the granite types, I types, S types, but the reducing magmas, that's the tin tungsten deposits. Affects the oxidation state of the trace elements and all. Tin are ones which become incompatible elements under reducing conditions, and therefore they can get concentrated up in the hydrothermal fluids. The opposite is in the highly oxidizing conditions for the copper and the gold and molybdenum. So the idea that our different classes are there, yes, and extreme conditions can really help concentrate things down. And then it gets into that issue of how the magmas, the primary composition of the magmas, and then how they're modified by crustal interactions. And just a little bit of crust or a lot. And then what type of crust. So Sumatra obviously sent the plutons off into the tin tungsten world. But New Guinea, we're in the world of copper gold. Different type of crustal contamination and modifying the fundamental conditions in the magma chamber and oxidation conditions. So yeah. Good point.
I think.
Okay, thank you, Professor.
Okay, thank you, Pak Budi. So we're going into the next question from Pak Haryo Pangaribowo. Maybe Pak Haryo, still there? So if possible to activate your video, is much better to directly intense communication with Professor Mark. So please, if possible.
Hi, Prof. Mark.
Hello.
Yeah.
Thank you for the presentation. I just would like to know from the opinion, because from the slide that you present to all of us here, based on the location in Papua, from your experience, is there any encouraging region in Indonesia that could there's a copper molybdenum potential deposit to be found, like in Sulawesi? You never mentioned Sulawesi before, as far as I know, but there's an exploration has been conducted there, and I think there's a potential for copper and molybdenum exists there. So what's the hurdle that explorations state not to be followed up there to explore the discovery.
Yeah,
Thank you.
yeah. What? Indonesia is an area where subduction zones have gone. Definitely the idea that everywhere is a possible place, I agree with. The issue is the conditions to set off a system so that it becomes mineralizing is the issue. I am convinced that you get the right chemistry, the potential right chemistry in lots of different places, but to get the right plumbing and to get the right fluid generation history is the problem. The right plumbing to get fluids separating at depths where you can get the concentration of the metals in the fluids, that is not going to happen everywhere. The issue of the rate of fluid generation, that's how long it goes on, and then you can focus the flow. That's also partly the plumbing issue, is that these factors have to all work together, work in concert, work together to, but the thing I think we've learned from exploration all over is that for every ore deposit, there are literally hundreds of intrusions which are very similar chemically. And the idea that only some of them get the combination of other factors together that can become mineralizing systems, and how to get the evidence that it's in the area. Well, it's the brute force exploration of stream out level geology. And obviously, the drill allows you to see past the soils and all that's out through there. But the idea that we have these different continental fragments in different parts of Indonesia as different basement, as well as subduction zones that over the last 400 million years have come and gone, I would say everywhere needs to be checked. I see no reason to immediately say it's not possible. So I think it's definitely plausible. I mean, Sulawesi region, Kalimantan, we have lots of areas that have had convergent margin geology. Therefore, the potential's there.
Yeah, I think Sulawesi is everyone will be agree with me, because this is the island of the formed from 3 subduction plates. So from the 3 plates, I mean, so it will be interesting for geologists to explore this area. As far as I know, correct me if I'm wrong, because this area, I think, is already being sitting here for maybe 30 years, because there's I think Rio Tinto started the exploration from the early 90s. They already bring the samples from blades, from soil and rock chip there, and it returned from 20 to maybe 400 ppm on for molybdenum. So that's the point.
That sounds excellent.
It's already 30 years, Prof. And I don't know if there already another company to explore this area, but that's the that's the interesting one.
Yes.
Okay. Thank
well,
you. Thank you.
One of the
Haryo.
things I have.
Yes. Thank you, Prof.
Yeah, thank you. One of the things I've learned about exploration and talked to many, many people in the last 30 years is how persistent one has to be. The many, many places that have been discovered actually had been explored before, but people didn't quite look the right way. The Porphyry in Papua New Guinea is one example. that particular deposit, 6 different companies had exploration programs around the target area before they actually found enough material to turn it into a mining deposit in PNG. So you got to be persistent.
Ya.
Oke, Pak Idrus.
Thank you, Pak Haryo. Ya,
Arif.
terima kasih. Ya, makasih. Thank you, Pak Haryo, for the question. Also, more insight in Sulawesi. And we are going into the next question from Pak Ian Wolf. Do you hear me, Pak Ian? Or,
yes.
Okay.
Yes.
Please show your video if possible. It's much better for communication,
Okay.
good communication. Yeah.
Yes. Good morning, Professor. Thank you. Simple question. Have you looked at unfolding the sediments to test your model of collision?
Have we done a structural analysis of the highlands? We've done the best we can with all the controls from the stratigraphy that we got out through there. So yes, we know there's about 20 kilometers of shortening in the passive margin sequence that you can do just by unfolding the folds.
Okay, so 20 kilometers. Thank you.
Yeah.
Thank you, Pak Ian. Thank you very much. So we are going into the next. Edward? Is there?
All right, thank you. Yes.
Yes, Edward, please. Yes.
Thank you, Pak Arifuddin, for giving me the right now. So, Mark, how are you? I hope you're
hello.
Doing great.
Good to see you.
Good to follow your presentation. So this is very interesting. And so before I give the question in here, I just want to let you know that maybe we talk about Grasberg as a huge deposit in Eastern Indonesia. So we have to appreciate also for our geologists in Western also, because after Grasberg, Batu Hijau, and after 2 decades, they discovery another deposit of porphyry in the Sunda Banda Arses. Also, you know that Tumpang Pitu and also Elang, and also maybe next the Hu'u deposit, and this is very nice, interesting. So we have to know that our geologists, and we have to appreciate for them for discovery. That's we have to know. So for the Grasberg in here, I want to give you one question maybe or two. Well, what is the best magma type for forming the huge of porphyry copper deposit? And the next question is, what's the special characteristic of Grasberg's porphyry system than other belt in Indonesian where has other porphyry deposit? That's it, my question.
Okay. Here is the magmas. If you want to make a characterization of the magmas of the Erzberg district, is they're shosenitic. They are relatively high in potassium, but everything else about them is not all that unusual. The unusual thing is the gigantic ore body that's associated with them. But my belief, and having looked at much of the Freeport regional exploration program, there are many dozens of other locations in the highlands of Western New Guinea that had very similar magma. It did not form ore bodies, or at least they haven't found them yet. The idea that there's something particularly special about these magmas in terms of their geochemistry, they got to be oxidizing, or else you're going to have things happen. You got to have enough sulfur. You got to have enough chlorine. But there's a pretty wide range, I think, when you look around the world at porphyry-type systems, that they can do it. They just have to be in the right range of conditions. The problem is the getting the fluids out at deep enough depths so that they're chlorine rich and that they're taking And that issue of having a geometry so that the fluids can then discharge in a small area, as well as have their chemistry evolve in a way that they precipitate minerals out, the ore minerals out, is the key thing. But there's nothing extraordinary about the chemistry. I think this is what we've learned from exploration all around the world is you get lots of plutons very similar. They call it the barren pluton problem. This pluton looks just like the ore body forming pluton, but there's no ore bodies. And what's the difference? Difference is in the nature of the intrusive setting, shape and geometry of the plutons. That's why I'm always drawing these stocks in the batholiths. If it's something that's different than that, you end up with, it's not going to be so likely to be able to focus the fluid discharge for a sustained enough time to make an ore body. The other one is you got to get the deep-seated fluids, but most systems, if you're bubbling up near the surface, you're heading to volcanic eruption, and that's no good. So I really don't think it's an issue of really special chemistry. You can have the wrong chemistry by too much carbon assimilated in the lower crust, not being oxidized enough or turn it reducing. But the issue of can you have the right chemistry and it just simply doesn't have a system, I think that happens all the time.
Okay.
If you can find a special ratio, if you can find a special ratio of elements like barium to strontium or something that tells us these are mineralizing systems and these aren't. But I know many people who've tried to do this and it doesn't work, or at least not in a way that really aids exploration. Maybe someone has better experience, but I know a lot of people who've been trying. It's what I call to find the silver bullet. The silver bullet is the special one, the special combination, but no one has actually found it.
Okay, I think it's enough for Pak Edward.
Okay.
So get the point.
Thank you, Pak Mark. Pak Mark,
Okay.
do you think there is any potential for the old rust belt in Papua? Because from your presentation, you thought the oil is eroded. I mean, if you correlate to Oketidi or correlate to Porphyry, there is a potential belt for exploration for another Porphyry-Type deposit.
Absolutely. If there's not other significant ore body somewhere in the highlands of New Guinea, I would be very surprised. They're hard to find. You got a lot of cover. Remember, you got the issue of ones which are buried under younger stuff, but the other ones are not buried. They can be very difficult to locate.
Okay.
Okay.
Thank you, Pak
I
Mark.
think enough.
And Pak Arif, thank you so much.
Okay, thank you, Pak Edward. So
Thank
keep
you.
healthy. So the next, we're going into the next, Pak Lukman Sutrisno. Are you still there?
Yeah.
Okay, thank you, Pak Lukman. So please express your question short and clear, Pak. Thank you.
Okay, thanks, Mark, for the presentation. I think I have one question. It's related with your concept of vertical pull-up within the pull-apart basin. Well, how do you reconcile between the brittle deformation of a pull-apart basin, pull-apart transtensional, and ductile condition around the intrusion complex, like shallower brittle ductile transition? Because in Sumatran arc, it shows that volcanic clusters are always located outside the pull-apart, intra-arc pull-apart basin. So how do you reconcile those two things?
Okay, very interesting. Volcanic cluster in Sumatra. This maybe I don't know enough of the specifics. Definitely, there's plenty of strike slip in Sumatra. You've got Sumatra fault zone, but there's also subsidiary splays, and maybe there's some even better studies that I do not know about that have shown some of the relationships. But back to the original question about the brittle versus ductile and pull-apart structures. Well, that's excellent. The issue is, it's true, up near the surface, fracture processes are going to dominate. And in a good pull-apart area, normal faulting is what's going to be expected until the magma gets up to that depth range. So rising from below, and then it can start to magma fracture and make dikes. So instead of normal faulting, you're going to extension fractures. Extension fractures just filled with magma, dikes. So that part is an evolutionary thing. I think that's quite common. The idea that it was extending until the magma, and then it became dikes, and then we're no longer having much in the way of normal faulting because the space is being accommodated by inflating the dikes. Deeper down, where it was always ductile to begin with because it was hot, that's how I think we get the dimples going on the tops of magma chambers. The idea that up near the surface it's really brittle, deeper down we have these step over connections and the rocks are flowing. The effect of stretching the roof of a magma chamber thins it. And if it thins it, the magma right underneath it's going to thin area a little bit. Depending on the total amount of extension will control how much of a thinning effect. But that's the beginning of a stock. And lots of places, that's all that ever happens. The stock only penetrates up into its ductile roof and cover. But if you got an area where the action is stronger, then it can start to get up to the point where it can actually fracture its way in. The magma fracturing, I mean, the simple principle is the pressure of the magma has to exceed the local sigma 3 plus the tensile strength of the rock. And so the issue is, well, where can that actually happen? Well, I think it has to do with speed of the overall system. If you got a strike slip system, which is working at about, say, 1 centimeter per year numbers, that's not very fast, but that's significant. The issue is in 100 years, you're going to have about a meter of offset that's going to build up. It has to be accommodated. But if that's being accommodated simply by ductile stretching, okay, we're thinning it. You keep that going for 10,000 years, it starts to add up to be significant. But if it's in the 1 centimeter per year kind of number, it's possible for that ductile zone to bulge upwards so the magma is there in position to then enter a fracture. And the real issue is the state of stress that you've got that's happening in the pull-apart zone. And if you get a large enough tensile stress, I mean small enough tensile stress, we can start to have the fractures, the magma starts to work its way up. And once that happens, the magma can start to wedge its way towards the surface. And I envision these things evolve over time. It's not going to happen in 1 year. It's going to happen in decades to thousands of years. But the intrusion comes up, and then the next intrusion comes up the hot ductile middle of the next one. The next one comes up that ductile middle. Next one comes up even farther because it's there, and eventually works its way towards the surface. And if you actually get to the point where it breaks out at the surface, well, then it's a volcanic conduit. And if it's a volcanic conduit, then you can start pouring magma up to the top, and that's going to heat the walls and make a ductile conduit. And from that point onwards, slugs of magma can continue to rise up the same path. And if you keep doing that long enough, the next thing you evolve to is make a volcano, a tall, towering volcano like one of the many in Indonesia. Focused magma ascent. But the issue is how to get it started. And that is where I think the faulting part of the story is the nucleator. But obviously, once it becomes fully mature, and if there's enough magma being generated from down below, it can just take over and control its own history as a magnetic center. So I think you hit on a very, very important question here. How to get these things started. And a little bit of motion doesn't do much. But how much do you have to have before it really takes off, and then it can evolve into a stock or becoming the center of a mineralizing system.
Okay.
Okay, thanks, Mark.
I think it's enough, Pak Lukman. Yeah, thank you. Okay, so just going fast to the next question from Pak Surya Nugraha. Pak Surya Nugraha is still there?
Yes, yes.
Okay. Please show yourself and just express shortly and clear, please, Pak.
Okay, thank you. Hello, Mark. I hope you can hear me. I still have to use mouse in the office.
It looks
So
like you're
I
in the
have,
laboratory.
yeah, I'm in the laboratory. I'm in Singapore, in the Observatory of Singapore.
Oh, excellent.
Interesting talk from you. And I'm interesting because I don't have a strong background in mineralizations, but I have a good background about the tectonics. And I'm interested about the model that you propose. And do you think that model can be applicable to other areas with the kind of a similar like collisional event? Because I can see that from one of your presentations, one of the main things that differentiate between the East and Papua New Guinea is there's a early magmatism in the Pliocene. And the following and the other model that the model that you also propose is the events of the delamination following the collisional event. How that can be very important. Is there any difference if the following of the collisional event is the other model, like for example slab break off, or even like extension that is related to, for example, in Sulawesi, that I know there are some metamorphic core complex that related to the rising asthenosphere.
Yes.
Okay. Thank you.
Excellent. No, I think the idea that did what happened in New Guinea happen in lots of other places, I think it has. But are there other variations? Absolutely.
Yes.
The issue of other factors that start to come into play has to do with how the local nature of the collision evolved. In the case of New Guinea, we went into this strong strike slip regime. We see it today. It's still going on because you got the Sarong, Yapen, Bawani, Torricelli fault zone on the north side of the island with all kinds of strike slip earthquakes. So since it's just happening, and why I think it's such an important place is we can tell what's happening. But is this how it's got to occur in all other places? No. The idea that in some areas we can pretty much go straight to a subduction reversal. In other words, the old idea that I was saying that people have argued for here, that you jam the subduction zone, but you still got to have the slab break off so that it gets out of the way for the reversal. But can it quickly evolve into that? I think it can, and I'm sure in some places it has. But the other converse is that whenever you have a collision, you've changed the force balance on the plate. So other things got to happen. And that's definitely also what's occurring in the New Guinea area. If you go east of the island, we have, in the last 3.5 million years, 2 other major spreading centers have opened. You got the Bismarck Sea spreading centers, that's since about 3.5, and then also the Woodlark, which we mentioned before. Those are all manifestations that over on the side, the edge, the side of the system, it's behaving different than it did in the middle. So, to take that in terms of, are all places going to be just like this? No. It's going to depend what's happening in the neighborhood. It's going to depend about how big of a collision zone it is. And collisions are definitely going to vary from place to place. If you've got sort of a promontory sticking off of a continent, jamming up a subduction zone in a small part of it is going to be different than a big straight margin entering a subduction zone, jamming it up, let alone all the other factors in the immediate vicinity that's there. So I see this as the collision story, as I tell it, is the #1 part of the story, the slab breakoff and the detail of why it involves the lithospheric mantle, which before was not part of the story. Now these people say this is possible. But other variations of how these things are going to evolve, absolutely. And that's, I think, is part of the exciting thing of going to the next level. The idea that this is the first order part of what happens with a collision, yes. But what are the details that happen afterwards? It depends where you are. It's sort of like at the beginning of plate tectonics, where you had what happens at a ocean ridge, what happens at a subduction zone. When we got the first order picture, but do we have the details of what happens next? No, in the case of subduction zones, some are accretionary and some are erosive. It took us 20 years to figure that out. But we now have a picture of the diversity of other behaviors that occur. And I think the same thing is when we go to the next level of collisional tectonism, the first order part of the story is the slab break-off, magma generation, lithospheric mantle involvement, and in some spots, it can set the stage for doing something spectacular in terms of ore bodies. But in general, it just is making magmas. And why we've got magmas up the spine of mountain belts all over the place, now we have an explanation. And before 20 years ago, this was very, well, where do they come from? Subduction reversal? No, these are collision magmas.
All right. Thanks very much, Prof.MarkCloos. It's very interesting talk from you. Thanks very much. I learned a lot. Thank you.
Thank you. And I wish I could go to my office like yours. I have to sneak to my office. I am officially not allowed to go to my office. I have to sneak in. Very strange life in Texas.
Thank you.
Thanks, Pak Surya from Singapore. Okay. So we just go into the next question from Muhammad Fahri Auladana. So are you still there, Fahri?
Yes, Pak.
Yes, please show yourself video if possible. No? Okay.
Okay, Prof.
Good.
Thank
Very
you
good. Yeah.
And I want to ask about, is there any possibility to form three elements or three economic commodities, copper, molybdenum, and gold at once? And is it formed from transition and evolving subduction and collisional? And is it possible to form in Indonesia outside the Papua district, for example, in Sumatra, Java, Sulawesi, or Kalimantan? Thank you.
Yes. Well, back to the last one is the issue of other spots in Indonesia. Absolutely. But are all places going to have them? No. The issue of you got to have the right conditions to get the fluids out. And if areas are too hot, one of the standard questions is, why do we not have porphyry copper deposits in Japan? Oh, there's a couple little mineralization sites that have started, but nothing that's a significant ore body. I think it has largely to do with that if the arc is in the same basic location for a long time, you end up with very hot conditions in the middle of the crust. You can never get the bubbling fluids that are metal rich being generated, because you got to have the right depth range to get chlorine rich fluids to cause this type of mineralizing system. So there are things that come, and that's overall why deposits are rare. We have in Western North America 200 million years of subduction, but only a few windows of time when ore bodies form. Same thing happened in South America. You got 3 main windows of time for Chile and Peru where ore bodies form, but you had 200 million years of time where it could have happened, but it's not. It requires having the right temperature conditions. It's associated with changes, and overall you want relatively cold conditions, I think is what I would say is number one there. But back to the metal combinations that I think was the first question. Can we have all three together? Yeah, some deposits do. The economics of some deposits is you get 5% of your money from the molybdenum and 10% from the gold and 85% from the copper. But various proportions can happen. But the ones where you've got true co-products, like it could be in Grasberg, could be, if there was no copper, it still could be a gold mine. If there was no gold, could it still be a copper mine? Yes, true co-products that you've got both elements in great abundance. But most of the time, the other elements are subsidiary. To me, one of the interesting things, though, is the subsidiary deposits around major things, because not just copper, gold, and molybdenum, but you also have lead and zinc. When you actually studied the fluid inclusions, those elements are there too, but they've been flushed through the system. And so the idea that in more and more places, looking for the subsidiary deposit of something else, because it's associated. But it does look like in most cases that the fluids just get dispersed. In the case of Grasberg, it looks like the lead and zinc that was in those fluids just came out in the hot springs at the top and just flowed down the mountainside. So there's a little bit of lead zinc, but not very much. But in other places, it could be a much more significant thing. But the idea that the metals separate in the fluids, that's largely because of temperature. So the temperature conditions to get things to precipitate is that distinctly different. Lead and zinc at temperatures less than 200 degrees, the copper and gold at the 450 to 300 degree range. So separates things out yet in another way, the filtering along the flow path. I hope that helps.
Very much, Pak.
Okay, thank you very much, Pak Fahri. Then going into the next from Pak Jarwanto, just make your question clear and short, Pak Jarwanto, please. Pak Jarwanto is there? Is no? Okay, the question from Pak Jarwanto, do you have type collision in Sumbawa Island? How different specifically from collision from Papua New Guinea?
We're talking about
please.
Sumba.
Sumbawa.
Batu Hijau.
Where Batu Hijau situated, yes.
Yes. I have never had the opportunity to visit. I've always wanted to go and see for myself. Definitely many, many similarities to Grasberg. The issue of what has happened there. Well, we are on the western edge of the Australian continental margin subduction story. And obviously the collisional aspect of things that's in Timor itself proper. Timor is what New Guinea looked like back about 10 million years ago. The geology in terms of what's going on is a little bit different because of changing structural style is a little bit different because of the nature of the stratigraphy. But basically there's our window that's there. My belief is what Batu Hijau is about is the beginning of a tear. It's the same basic story, that we're in the earliest stages of a slab breakoff associated with it. And it so happens right at the beginning, it doesn't take long, but we are within the million-year time window to become mineralizing. So I see the parallels there. I also hope that someday more geophysics is done around the island to understand the details of what's happening down underneath the system right now.
Okay. Okay, thank you, Pak Mark. So just quickly going into the next because the time. And from Pak Agus Purwanto, please, Pak Agus.
Thank you, Pak Arif Idris. Agus Purwanto from Tujuh Bukit. Pak Mark, based on the difference of two kind of the copper system, which is copper gold and copper moly. If there is surrounding that area any epithermal mineralization, is this will be any difference kind of the epithermal style, but of two different porphyry?
I did not quite hear. Please repeat.
If in the porphyry copper gold and copper moly, there is any epithermal mineralization, will be a different of epithermal type of both of two different porphyry?
Yeah. Yeah, very excellent question. Yes, the issue of the epithermal parts of the system. No question about it. In some areas, that's substantial. As I was saying before, the issue is epithermal lead zinc, but the idea that these fluids, as they're coming out, if they've actually got a fair amount of gold in them to begin with, there's no reason you can't have a good epithermal gold deposit. And with basically no copper, is that if you got plenty of sulfur in the system, you can dump all the copper out, and the fluids become almost zero in their copper content, but they can still be moving the gold, the leftover gold. So that idea that we end up with the superficial hot springs and things of that nature, and we still have gold mineralization is residual. We don't completely run out. The reason for it is the efficiency of the copper precipitation is rooted in what sulfur's doing. And if you got the water hydrolysis reaction of SO2 and all, you can make all the reduced sulfur that you need, and that can be completely enough to strip out all the copper. And then but gold still has solubility, and it will precipitate out as native gold. Yep. Silver too.
Yeah.
Okay.
Thank you.
Agus is enough, I think so. Okay. So the next, very quick, from Pak Sahreja Angkasa. Are you there,
Yeah,
Pak Reza?
yeah, of
Sahreja.
course.
Okay.
Of course.
Yes.
Hi, Mark. It's very excellent presentation. But I have a question about your model a little bit. How you explain we have many multiple intrusion in a porphyry copper deposit, but how you explain with your model? Because if I saw your models, there is a fractionated magma reservoir there. And because I'm a volcanologist, I study Tangkuban Perahu and Ijen volcanoes, I saw many signs about replenishment of mafic magma in the magma chamber. So it will be very useful for constraining the time of the beginning of fractionated magma to release the intrusion, I think. And my widely interpretation is your model showing that the volcanoes is almost dying, I think, when you can preserve such a big amount of fractionated magma in the magmatic reservoir.
Yeah, excellent. And what you've now got something is that we actually have, I have never given a presentation on this, but we have a lot of understanding in the Erzberg-Grasberg district about magma chamber recharge. The issue of that parental magma chamber was recharged multiple times.
Okay.
The idea that it just has one history, no, it's actually multi-stage history. The way we know it best is from the isotopic fingerprinting, particularly neodymium and strontium, but also supported by lead isotopes. But what we can actually see in the district is there's the oldest magmas, which we've now get. By the way, we have over 130 igneous bodies in the district dated, and we got isotopic fingerprinting on about 80 of them. So we have a tremendous data set now, which maybe next year, maybe this fall for my presentation, I will show it for the meeting. But the issue of the system started, and then the magma chamber, the system got recharged and reset the isotopic systematics with a larger fraction of asthenosphere to lithospheric mantle or crust component in it. So that pulled the numbers off in one direction. It then set off the Dahlem phase in the Grasberg. There is a little pulse of mineralization in Dahlem, and then there's a magma chamber recharge event, which reset the isotopic thing. It had to have been enough magma from down below, and it had to be enough convective mixing to turn off the initial mineralization phase. And then we have the plug of the main Grasberg intrusion that comes in. We then have the main mineralization event that happens in it. But then there's another magma chamber recharge. And I think the effect of the magma chamber recharge is to heat up the system and turn off the bubbling. So it ends up stopping. We then have a thorough remixing, and then we have the Kali phase of intrusion that ends up happening. It postdates the main mineralization part of it. Then we have another magma chamber recharge event, which resets the isotopic system. And then we end up with the main Erzberg intrusion. We've also got several other dikes and sills and all that poke their way up as different stages along the way. But there's no question what you were bringing up here is it's replenishment in slugs of magma from down below, which can be enough to turn off the mineralizing system. And I actually think what we've got is multiple cupolas, multiple sites, and over time, the mineralization jumped around, associated with starting and stopping the whole story, all rooted in the recharging that's happening. enough heat, enough magma has been to reset the system. We can see it isotopically as a direct fingerprint. We can also see it from the fractionation sequence when you look closely at the petrology of the different intrusive phases. And then the last thing I just wanted to add to this is the comment about volcanism. The idea that we have to have volcanism at all to get mineralizing systems, I'm absolutely convinced, no, you don't. It can happen, but it doesn't have to happen. And in the issue of the Grasberg itself, we got a little bit of volcanism associated with the Dahlem phase and the first phase of mineralization. Yeah, probably never much more than a Mar caldera, always low relief, not much volcanism, but there was some. And then it became a mineralizer. The MGEI phase, which is the main show, probably 85% of the ore in Grasberg, no evidence of any volcanism. No reason to believe there was any volcanic component. Same thing goes with the Erzberg pluton. There's a good 800 million tons of ore, a porphyry-style mineralization. No evidence that was associated with any volcanism at all. And then the capper, the major part of the story is we have 4 different skarn systems, all geochemically related. None of them are associated with volcanism. So the idea that volcanism is essential for doing this, no. But can it? Absolutely. So there's my sort of highlights of some things that's coming. The Erzberg-Grasberg district still has more things it's releasing in its secrets. It just takes a lot of time to process all the stuff. So it's coming.
Well, thank you very much, Mark.
Okay, thank you, Pak.
Thank you.
Pak Sahraja, thank you very much. So we still have 3 remaining questions, Pak Mark. And I see you still enjoying answering the question very much. So the next
questions are so good. I like the questions. They make me think. I liked it.
Yes, yes, I see also. Okay, just quickly going into the next question from Pak Dadan Wildan, but because of the speaker technical problem from his speaker, I just read his question, Pak Mark. Dear Professor MarkCloos, we know that all of the deposit found today is basically originally coming from the hydrothermal fluid coming up to the surface. Do you believe that if today we could define a hydrothermal source which carries the economic element, then can be extracted today, for example, from the geothermal fluid and so on? Maybe this is like a shortcut for mining process.
Interesting question.
Yes.
And one of
yes.
the idea that direct processing the hydrothermal fluids and getting ore, it can be done. It's not a porphyry system, but in California, in the Salton Sea geothermal area, they got lots of lead and zinc. The fluids, it's a problem of scaling of the pipes. They really want the hot water. In Indonesia, I am aware at Merapi, people have sampled the vents, and there's lots of metal. And then, of course, now with White Island, which is really where some of the very first studies were done, the idea that the fluids coming out now actually have enough metals that if you just did it long enough, we can make ore bodies. Absolutely. But to actually have economic stuff right now from, in other words, you capture the fluid and put it in a pipe and send it somewhere, I don't think you're getting very much. The idea that if you could capture it all for 1,000 years, that would be good. But in a period of 10 years, I don't think you're going to get very much. But is there plenty of metal that's dissolved? Yes. And that's been one of the exciting discoveries of the last 20 years, is that many active geothermal fluids actually have plenty of metal.
Yeah. Okay, thank you, Professor Mark. Next is from Pak Rusman. Pak Rusman Rinawan, our senior also. Pak Rusman, are you there? Okay,
yes,
thank you, Pak Rusman, please.
Dear Mr. MarkCloos, I thank you very much for your lecture. And my question is, where is coming from the original of gold, copper, and molybdenum, and how is going on to be enriched in magma generation? Thank you.
In terms of original, the original source.
Okay, please.
You're
right.
Well, that. I am. Yeah. Well, the great debate has long been: does it come out of the crust and then in the magma chamber get concentrated somehow by fractionation, or is it in the primary magma? And in the long time ago, the idea that the magmas are generated in the crust and some areas of crust have more metal, therefore these make ore bodies. I don't think that is the way to look at it now. The issue of, do we have metals in different concentrations in magmas? Yes, but the bigger thing is the amplification of getting the metal out. And that is the fluid story. And so if you got the right fluids, you can get the metals coming out at a much higher ratio, distill the magma, distill the stuff into the fluid. And that is the element, essential element of doing most of this, is that you get the concentrated fluid. In the porphyry-type, epithermal related types of deposits, we have lots of fluid inclusion studies that tell us we can get these fluids very concentrated. And the number one element for helping that happen is chlorine. If we did not have chlorine, you're not going to nearly do it, but the chlorine complexes are the critical thing. So the issue of concentration, do the magmas have to be very special in their concentrations? No, but if the fluids are coming out and the metals are going into the fluids, then they become concentrated. The next part of the problem is to precipitate the metals in a small area to make an ore body. If they're dispersed, or if they go out of a volcano, no, it doesn't help. But if they get dispersed too much, then it's not as low grade ore. You want to have it concentrated. And so that's the precipitation part of the story. And that's the combination of temperature, that is how temperature gradients, very strong temperature gradients, small area precipitation. Another one is reaction. As the fluids react with other fluids, we can get localized precipitation. Or my favorite are the skarns, where the fluids hit the carbonate rock and almost instantly change their chemistry because of neutralization, and therefore can precipitate a lot of metal in a small area, let alone make the space to put the metal by dissolving the carbonate. So those are what I think is the special things. Is it possible that in some cases an ore body happens because it happened to hit another ore body deeper in the earth that was buried and get remobilized? I'm sure it's happened. I just think it's rare.
Okay, Mr. Mark, that I mean the original of the gold, copper, and molybdenum is coming from lithosphere, or maybe asthenosphere, or maybe coming up from the mantle. So by plum or super plum and related to plate tectonic. That I mean, how is going on? But there. Thank you.
Yeah. Okay. Maybe I guess I did not quite hear I did not quite understand, but the idea that one of the elements that moves around in the small degree melts in the mantle is gold. I don't think there's much question about that now. So if you got areas that have a little bit of partial melting going on, remobilizing that small amount of gold in the mantle, but then reprecipitating in the lithospheric mantle, that looks like it's happening. We also have the story of the fluids going down subduction zones, things getting dissolved. We have the ones that come up the volcanoes. We're talking about those right now, but some of them get passed, and those are remobilizing elements that are dissolved in those. But back to the original point, where did most of the metals come from? Most of the metals came out of the mantle. And the issue of if it's coming out of the lithospheric mantle, it's got a high gold to molybdenum ratio. If it's coming out of sediments that got subducted deep into the mantle, well, that's where we can have the added component from high molybdenum to gold, which then once in the magma can get redistributed in the ways we were talking about before. but copper is always somewhere around that 50 parts per million number. Oh, 25 maybe, 75 parts per million, but it's very, very rare to get that because it's just quite evenly distributed out there. But that's all it takes.
Okay.
The primary magma for Grasberg was probably about 50 parts per million copper. No evidence at all that it was a copper-rich magma anywhere in the district.
Okay, I think it's enough, Pak Rusman. Yeah.
Okay, thank you.
Thank you.
Terima kasih,
Okay.
Pak Idrus.
Okay. Thank you,
Excellent.
Prof. Mark. And we are going into the last question. I think the question coming from Pak Bustanuddin, and I see the name of Pak Bustanuddin, the similar questioner. Pak Bustanuddin, are you there? Okay. If not, I just read the question from Pak Bustanuddin. Is there a relationship between the type of mineral that form in the subduction zone with the type of colliding plates? So the type of mineral in the two type of the tectonic setting, please, Prof. Mark.
In terms of the minerals
yes,
that are forming? With respect to copper, it's mostly a story of chalcopyrite and bornite, cobalt, but in terms of all the minerals of the copper world that it could be, it's almost entirely those three minerals. When you go to supergene environments and things like different, many, many more can show up. But if we're talking about magmatic fluids, high temperature hydrothermal systems, that's mostly it. There's a few other oddballs, but that's it.
Okay, Prof. Mark. So, Pak Bustanuddin, do you have any feedback? Okay. So I think he doesn't hear me. Okay.
Is attended.
Okay, please, Pak. Okay. Okay. I think enough for this session. I have to thank for Professor MarkCloos for this very amazing question and answer session, and I'm going into the closing session. And before I'm go to the Pak Budi as chairman of the MGEI, I think I give opportunity to Professor Ben Sapii. Maybe some word that you would like to express, Pak Ben.
Thank you, Arif. I just want to say hi, Mark. How are you doing?
Oh,
good to see you again. Good. It says excellent as always. So thank you very much for MGEI to invite him all the time. So I will enjoy the conversation now for now. Hopefully to meet you again.
Yes.
Pretty soon, Mark.
I hope so. I hope the world comes back to the new normal, as they say.
Yeah,
and the new normal for all of us is to do our field work and do our exploration, and obviously, this is a very, very strange time. But I do think overall Indonesia is doing better than we are. In Texas here, August 15th. I'm not supposed to go back to my office until August 15th.
Yeah, same thing too, because they not allow 55 years old to coming back to school until August 1st or something like that in here. So I have to stay at home too.
Well, we
Thank
all
you
have
very
to be
much.
safe.
Good to see you again. Thank you very much, Arif, for the time.
Okay, Pak Ben, thank you. So actually, MGEI would like to challenge you to also share to us for the new generation. But maybe Pak STJ would like to say something to Pak Ben in this good event.
Yes, of course. I was intrigued by Professor Ben's comments on the last Professor Mark's presentations. He said he was actually posting questions about where do we actually have to explore in Indonesia if we want to discover another big or giant targets. And he said something, yes, I know, but I will not tell you about that. So we would like him to share with us, maybe not now. We could have a very special session, Prof. Ben, if you like, and then you could share your thought about that topic, because today's topic is more about tectonics, more about tectonic settings. That I do believe that you are one of the best experts in Indonesia as well. So we would like to have your comments, Prof.
Okay, maybe I will prepare something someday. Yeah, but it's yeah, I just come back from the administration to become more lecturer again. So it's time. But COVID-19 coming in, so I don't have time to do much in the field yet. But yeah, but there is maybe MGI or other guys is no, because I have a gift from Pak Sujatmiko, the James person who like, and then there is Bornat and chalcopyrite samples that he used for the gift or for the Jamestone promotion. He mentioned that he came from Tasikmalaya. I don't know. I didn't realize this Tasikmalaya we have that such a, because when I see Bornite, chalcopyrite, and big chunk of others constituent there, I always refer to Grasberg, Mark. So I think there is a similarity here in the term of mineralization with Grasberg, but there is no big porphyry so far in Tasikmalaya. He mentioned to me that this is still in the mining, which is not illegal mining things, is not formal. So I would like to go there. So that's why if I have an idea there, but I always believe structure is the most important part to this issue. So I don't know, Mark, you still believe that chemistry is okay, but structure is the most part of the story. So.
That's definitely the perspective I have developed over all of these years and talking with many people. You get the right chemistry in lots of places, but you don't get the right plumbing. The issue of the plumbing is the problem, and then you got to have the right temperature structure too. But plumbing is the essential element which is missing much of the time. And the idea that structural control is a common thing is evident from the fact that when you get deposits, often there's trends. They occur in lines. They occur in clusters. The issue of something's going on. Well, that is the plumbing. So yes, same thing holds for petroleum too, except for shale. Shale oil,
right.
find the beds.
Okay, thank you very much for sharing. So.
Yes, thank you, Prof. Ben, for some word from you. Okay, I think so. We are going into the closing session, Pak Budi, Pak STJ Budi Santoso. So I think so my role is enough. I apologize if there are any mistake that I made. Thank you for you who still stay tuned in this, and also for who already left the session. Thank you. I give back to Pak Budi or Ocha.
Yes, for me,
for the closing remark. Okay, yes. Please. Thank you.
Thank you, Mas Arifuddin. You've been doing a great job trying to keep Prof.MarkCloos enthusiastic of answering questions. Yes, that's something we need to close the session very soon. But I think the lesson learned that I would like to challenge everybody who attended this session is actually to implement or to see if in our background, is there anything that we could apply, anything like what MarkCloos presented before. It's not just thinking that the copper moly deposit was actually only in caldera, but also somewhere maybe in the north arm of Sulawesi, especially in the small portions of the arm. and also in the West Kalimantan. Something that is very important to mention as well here is that, you know, I think, Pak Mark, here in Indonesia, we learned a lot about the tectonic setting of the porphyry, promoting by somebody like Richards, Steve Garvins, and Adi Marion as well, where they are talking about the jam or interrupted subduction process, flattened and torn slabs, and then that would make you know, big deposit or deposit of form. Something that we learn from Tujuh Bukit, maybe who is still part of it, and also Elang, and also a similar case in the Philippines, and also in Peru and Chile, something that interrupted the subduction process. We could still combine and challenge to them, to the writers, for sure. One thing that is very new, or quite new, is actually the roles of the sediment, the pelagic, the hemipelagic sediments of the Moli. There's something that I really, I didn't really consider that as a very, very important roles until today. So that's going to be very, very good food of thought, of brain. So actually think about that again, whether in Indonesia, we could find something quite similar to that when we talk about a possibility of having moly or copper moly porphyry deposit in Indonesia, which is we have some prospects found already. Okay, I think we will be ending this session. I recorded the participants were 192. It was very interesting to have that amount of persons who were interested in the subject, especially in the very early morning, 7 a.m. during the new normal. Maybe the new normal, the 7 a.m. is too early in Indonesia. It's usually not, but now maybe it is. Thank you very much once more to Professor MarkCloos. We will be inviting you again, Prof, to be our one of our keynote speakers in our next annual convention that will be held in October, with the same or similar format like this one, but it will be designed in a more professional way of having the session. It's not like the one like it now, but it's something we are still working on that. And of course, we want to make sure that we have also a well-known professor like Benjamin Sapii. I know, Prof. Ben, you've been working maybe too much in oil now, but we know that you've done a lot of great job in grasswork. So I think we will send an invitation to you to request your availability to be one of our keynote speakers for our next event, sometimes in October, Prof. Yeah, you have about 3 to 4 months to prepare your paper. I'm pretty much sure that's more than enough for your caliber. So I think that's I would think that that's going to be the case. We will have 2 keynote speakers, Professor MarkCloos and Professor Ben Sapii. So you could again meet your old friends, your old dear friend, Professor MarkCloos, the same stage or podium, if you like. Okay, now we have 87. I think The committee of the annual convention of the MGEI would like to share a video of this, a teaser video for the event. So I would request about less than 5 minutes of your time to attend the video sharing. Maybe Lina, before we officially close later on after the video. Thank you.
Okay. Hello, everyone. Yeah. This year, we will hold 12th MGEI Annual Convention 2020. And we come in different space, but still in the same spirit and warmest smile as past year. Yeah, MGEI Annual Convention will go virtual. We bring you all the topic about strengthening discovery and mining culture. Welcome tomorrow. So take a look for our video, please. Right, that's all for me, and thank you for your attention.
Okay, thank you, Mbak Lina. So the theme is strengthening discovery and mining culture will come tomorrow. So basically, we want to strengthen our discovery and mining culture, Prof.MarkCloos and Prof. Santai. So if you have any thought about topics that you could fit in that big topics, that will be a very great opportunity for us, the Indonesian economic geologists, to learn from the expert. So yeah. Okay, Pak, I think I would like to once more express our gratitude on behalf of the organizations and the Society of Economic Geologists in Indonesia. Thank you very much, Professor MarkCloos, for your time, for your effort, and your enthusiastic way of answering and question and encouraging us to learn more and to find more ore deposits in Indonesia, with all of your positive and challenging comment this morning, and also to everybody that has participated the session, so that the sessions went very dynamic, very productive, and I do believe that there are so many things that we could learn and take it and then implement it to our daily work or activity. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. See you in the next SASAMI session. Thank you very much.
Waalaikumsalam.
Thank you, Pak.
Thank you,
Thank
Pak
you,
Mark.
See you.
Thank you, Pak Mark.
Thank you. And
Selamat malam, Prof.
Wish everyone in Indonesia the best of luck in these difficult times. And certainly looking to when the new world comes back and we can all do the things we used to do on a regular basis. But Indonesia is a special place, and I feel fortunate to spend a lot of time there. So looking forward to a return someday. So thanks so much.
Thank you, Pak.
Thank you, Mark.
Thank you.
Bye.
Terima kasih panitia, sampai ketemu lagi.
Terima kasih Pak Ben.
Ben, jangan lupa presentasinya.
Insya Allah, ya.